各位贵宾，大家好，欢迎莅临未来科技奖创新亮点技术发表与商机媒合会。每一年度的未来科技奖聚焦于全球趋势、创新科技，成为学员团队展示成果的最佳场合。2025年的未来科技奖迎来超过500件技术头奖，最终有83件获奖。许多团队因此获得专利，或是荣获多项国际奖项的肯定，并在实际场域中应用。今天我们邀请到优秀的团队亲临现场，为大家介绍精彩的研究成果。本场次以生技新药、医材、先进材料与化工、绿能环保与近邻科技为主题。同时，今天的场合也是您与前瞻团队面对面的绝佳机会。待会的活动会分成2个阶段，第一个阶段先由8组优秀的技术上台发表，第二阶段则是1对1的媒合时间。我们会先以事先报名好的企业朋友们优先洽谈。若您听完技术后想要进一步了解，可以上线我们的工作人员登记。我们会在视状况替您安排，谢谢。好，相信各位跟我一样非常期待知识能量满满的发表会。首先登场的是生技新药领域，我们邀请到中央研究院生物多样性研究中心江英如研究员兼副主任。他将为我们发表雄激素代谢益生菌之创新开发，针对高雄激素血症的功能性肠道微生物疗法。我们欢迎江副主任上台。
各位朋友，大家好，我是江如研究员，目前任职于中央研究院生物多样性研究中心。那我们团队开发了一个新型的功能性益生菌，这支益生菌呢，可以透过代谢我们体内雄性素来解决高雄性素相关的一些问题。那我们团队呢，主要是由我的专长是厌氧微生物学，那我就负责肠道菌的分离、鉴定、培养，还有后续的一些生理跟代谢的分析。那另外一个主要的合作对象呢是台大医院妇产部的陈美洲医师，他是不孕症的专家，他最大的功绩就是帮动物园的团团跟演员做不孕症的治疗这样子，所以后来就产生了团员哦。那他负责的是临床样本的收取啊，还有这个小鼠实验的一些确效。那我们技术优势呢是用最实心的所谓多体学技术进行这个功能性肠道菌的开发。那我们首先用培养体学可以快速也大量的去筛选一些目标的菌株。那接着我们针对这些目标菌株呢，使用多层次的分子技术，从基因体到代谢体学的分析，就可以找到相关的一些功能性基因跟酵素。那找到这些基因有什么好处？找到基因，我们就可以针对这基因去找出更多功能性更强的菌，就可以一直累代的去那个开发，有点像这 iPhone 的系列这样子。那最后透过动物的确效，这目前已经完成了，我们用小鼠模式来进行这样。那目前正在申请临床的测试。这是我们团队最需要的那个资金挹注的地方，就是进入到临床的测试这样，而不是只限于健康食品。那我们叫做高雄性素血症，顾名思义就是我们体内雄性素过高，那这会有什么表现？在男性就变成射物腺肥大、射物腺癌，以及雄性秃。那雄性秃不是只有男生会有，其实女生也会有。哦，那另外在女生就会表现成多囊性卵巢症候群。哦，这大概是很常见疾病，将近1/5的女性都会面临这样的问题。那目前最主要的疗法是采用荷尔蒙疗法。哦，但荷尔蒙疗法会有很多副作用，包括这个性功能障碍啦，或是外观的改变啦，乃至一些心理层次的问题，包括忧郁啊、焦虑。那另外呢，在2年前的 Science 这篇论文里面，他有强调说，这个荷尔蒙疗法长期使用会让患者的肠道菌相失去了平衡，然后最终在治疗后期反而会让那个状况恶化。好，那很多人就觉得纳闷了，我们的这个荷尔蒙是在女生的卵巢或男生的睾丸或射物腺产生，那这肠道菌跟荷尔蒙的平衡有什么关系？这个其实 关键就是所谓的肝肠循环。我们知道说我们人体会有必须的那个荷尔蒙，就是睾固酮。睾固酮女生也需要嘛，因为那个你如果要制造雌性素的话 ，aromatase 这个酵素是用睾固酮当成受质。那睾固酮会被人体的5α reductase 这个还原酶呢转换变成双氢睾酮。那双氢睾酮可以把它简单视为一个坏的那个雄性素，为什么？它雄性素活性非常高，是睾固酮的5倍以上，5到10倍之间。那很容易造成我们体内的雄性过量。那双氢睾酮它会透过肝肠循环，最终跑到肠道去，所以我们可以用一些肠道的益生菌去代谢这些双氢睾酮。那代谢机转是透过一系列的还原动作，把双氢睾酮首先变成必须的睾固酮，或者进一步再把它转换成雄烷二酮，这就弱很多的这个雄性素，所以可以让这个雄性素的当量大幅度的下降。好，那我们近期的目标是开发健康食品，所以我们就从我们菌库里面去找有哪些菌是符合这个食药署正面表列可作为食品用途的菌株。那很幸运的，我们找到一株叫凝结芽孢杆菌，这芽孢杆菌它具有非常显著的代谢双氢睾酮 DHT 的能力，但是对人体必须的雄性素、睾固酮还有女性必须的黄体素这个生殖荷尔蒙没有显著的影响，所以它专性很强，所以只会针对双氢睾酮这坏的雄性素来代谢，但是对我们其他荷尔蒙尤其必须的不会有任何的显著的影响。那这支那个凝结芽孢杆菌呢，还有一些特性，包括它产生内孢子，然后具备耐热的特性，这对通路以常温来保存是很重要的哈。那另外它有耐胃酸跟耐胆盐的功能，所以它很容易就可以穿过这个胃，然后到达肠道，然后进而发挥它的效益。那所有的这个微生物都有一个所谓的 type strain 呢，就代表菌株。那我们从那个双氢睾酮去找出它的代表菌株哈。这个参考菌株也发现它没有显著的代谢双氢睾酮能力。其实我们手边测试了这个台湾跟国外的许多将近20支的凝结乳酸杆菌，其实只有我们的菌有这个特性哈，所以这个是一个非常特殊的菌株。那我们透过功能晶体学找到相关的代谢一个机转跟功能性基因。那小组实验方面呢，因为我们论文有发表关系，所以我们只有呈现比较简单的一些比较这样子。那我们分别对公鼠跟母鼠做测试。公鼠比较人工一点，就是说你必须要先把它背毛给剃掉，剃掉之后透过腹腔去注射双氢睾酮。OK， 那可以发现注射双氢睾酮之后，相较于对照组，它的毛发生长明显迟缓。但是如果过程当中除了腹腔注射双氢睾酮，我们还使用我们的菌株 BRCS-C3 这支凝结芽孢杆菌的话，你可以发现它的毛发生长其实就恢复了。那这母小鼠的测试其实是比较自然，而且是那个陈美洲医师真正的专长哈，就是说母小鼠它很有趣，它在透过高脂饮食的时候，它不只会变胖，它会掉毛。所以有时候你在路上看一些女性，她明显就比较胖，然后那个头发会比较稀疏，它很明显就是其实有所谓的 PCOS 多囊性卵巢症候群的症状哈。好，那你可以发现说，如果我们没有给益生菌的话，它脱毛会很明显嘛，除了肥胖之外。但是如果你在给高脂饮食期间呢，同时也喂给它这个芽孢杆菌的话，你可以发现它虽然也会变胖，但是它毛发会很油亮哦。OK， 所以透过公鼠跟母鼠的实验，我们就确定了说，这个凝结芽孢杆菌它对于那个动物脱毛或人类落发，应该会有非常显著的一个促进的功效。那我们目前已经完成了相关的技转，然后技转给2家厂商，包括这个金影生技。金影生技是南部的大厂上市柜公司，那他们的专长是做国内外这个益生菌的代工。好，那他们去年技转之后，其实很快就完成了那个大规模发酵。那他们有一些特殊的专利技术，包括包埋技术，还有一个冷冻干燥的速冻技术。这很重要，为什么？因为很多肠道菌其实绝对厌氧的，它碰到一丁点氧气，它就会失去活性。所以在做这个肠道益生菌的这个发酵跟适敏制备，其实有相当的难度了哈。OK， 那所以我们目前已经开发了这个产品的原型这样子。那有兴趣的话，可以去我们的柜台看一下这样子。好，那我的报告到这边，谢谢。
谢谢江副主任，请大家给他鼓掌，请回座。第2位我们邀请到的是国立成功大学医学院沈延胜特聘教授兼医师， 他将为我们发表通用型低免疫原液体 iPSC 种源库，实现再生医疗产业化与临床突破。让我们欢迎沈教授，谢谢。
以下各位来宾，大家早安哈。那我是成大医学院的沈延胜老师。那我们的题目主要是我们要发展一个，对不起哈，我们要发展一个通用型低免疫抗原性液体的 iPSC 种源库哈。那为什么哈？待会我会细讲哈。我们最主要实现我们再生医疗产业化跟临床的一些突破。那我们都知道现在是全球老化哈，老年人口大于65岁的急速上升哈。现在大概会台湾已经超过18%。那年龄老化以后，高龄社会来临，相对带来很多退化性的疾病或一些老化所带来的相关疾病。那如果我们在2025年进入这个无龄世代的话，大家可以看到，这个高龄我们在台湾已经在接近20%。那未来在2070年会达到70%，也就大部分都是老年人。那这样我们一些退化性疾病，你要怎么来治疗？我们不可能就是一大堆都卧床的人嘛，哈。那我们可以知道，高龄社会来临呢，我们有些这些医疗市场，我们现在叫健康产业，不能再说医疗产业，说健康产业。这个健康产业的产值会从43.8亿增加到213亿，也就是说，你有很多的医疗产品都是要针对的你的健康的问题来给予啊，所以说这个健康的产业从医材到医疗，很大的一个市场，它的产值相当大。那我们要发展这个 iPSC 的，我们叫万能细胞哈。那基本上大家都知道，最近细胞治疗很流行哈，你有属于干细胞治疗的。也就是一般的我们在癌干细胞，或是多功能干细胞，或是成人性的干细胞。另外有一些非干细胞的治疗，包括是免疫细胞的治疗，还有非免疫的。那这些治疗，你就像说，你未来可能像药物一样，每个病人给他标准治疗呢，或是每个病人不一样，给他不同的治疗，就是精准医疗。但是在今天，大部分的这个细胞产品是来自于病人自己的身体的细胞也就是我们特管办法所给予的这个细胞自己再培养出来，所以它必须要很高的成本，培养成本。那如果你要做成像一个药一样，那你的怎么来减少这个成本？这是非常重要的，在未来的这个再生医疗的产业要考量的啊。那 iPSC 还是可以解决你的细胞来源的地方，你不可能每个病人到老年的时候还是抽他的血去做培养嘛，所以你一定要一个像药物一样有一个细胞库来供应这个需要。那这个就是一个 inducible 的干细胞。那它有几个问题必须要克服了。第一个是不是会有免疫排斥？我们知道我们人的细胞跟不同人的细胞会碰在一起会有排斥的问题，所以我们第一个可能要考虑的是排斥的作用。第二个是假设你自体的培养细胞，我刚刚讲通常你要3个月以上，那你培养这个细胞你要花很多的成本，特别在这些培养液的花费上会很高。那再来就是假设你要用到一些编辑的技术 ，gene editing 的技术。那gene editing所用到的东西，你还是要考量能不能通过法规，所以它有很多的问题限制了 iPSC 在我们目前再生医学的使用啊。那在成大医学院，我们就发展了一个，我们针对我们老化未来的高龄年龄的时代来临，我们必须克服3个问题。那我们有培养特别去开发的这些干细胞的培养基。我们要开发这些一个 inducible 的干细胞，而且呢尽量能够低抗原性的。那我们要再利用一些编辑技术，可以克服我们如果把病人身上的这些单一基因的突变的，把它correct回来以后再种回去哈。那我们的解决方法就是我们发展一个通用型、低免疫型的液体性的 iPSC 细胞库。因为等于我们在做药都知道，我们药都是大量生产嘛，要储存在那里。一样，我们假设有一个低免疫型的这个抗原库，这个总 iPSC 的细胞库在那里， 我们病人有需要，我们就要分化到他有需要的细胞，再给他种回去就好。因为它是低抗原性的，所以你要使用的抗排斥药就低量就可以了啊。那我们成大目前已经有建立心肌细胞、神经细胞、免疫细胞，还有间质细胞 MSC 的细胞库可以分化到这个程度哈。那这个简单看，我们的这个 iPSC 液体的 iPSC， 我们已经通过的细胞形态、它的 polypotency， 还有它的分化能力，它可以 capture 的 Senda 的 STR， 还有 PCR 去证实它有这个能力。那我们的细胞的 cell flow cytometry 证实说，我们这个 iPSC 都已经有完整的 QC control。那为什么这个低抗原系这个很重要？我们的特色在哪里呢？是因为我们的细胞里面，我们让它表现出高的 HLA-G 跟 HLA-E， 那这两个 HLA type 1的这两个刚好是可以让我们的抑制我们一般产生排斥作用的HLA type 1的一些排斥反应，那它会让它的反应减小，让这个细胞可以活下来。那这是我们在我们做这个低免疫抗原性的 T cell 跟 NK cell 活性的测试，大家可以看到我们这个 HLA-E 跟 G 比较高的细胞，那基本上我们体内的 CD8 就会比较少。CD4 也会比较低，对它的排斥就会比较低，那它就比较不会去抑制这个免疫细胞这个 iPSC 的生存。好，那这是我们在动物实验，我们在刘元文教授，我们全世界有关于心肌再生的移植，大部分的 paper 都是我们成大刘教授所产生的哈。那大家可以看它的抗排斥药，只要用到比较低的每公斤2.5 ml 就可以有达到高抗原性的，高抗排斥药下的作用，它同样可以生存。那它的 cavalin 3就是代表它的拮抗那个心肌细胞的我们有 get junction 的反应哈，还有 CTNT 的染色，代表我们在这个有 HLA 的这个高跟 HLA、G 跟 E 高的话，它可以表现比较好的这一个心肌细胞表现在它植入的在动物的身上哈。大家可以看到它的 graft 生存就比较好，然后这是它的心脏功能哈。我们在只要低剂量的环孢磷 A、cyclosporin A， 这是心脏移植最常在用的 cyclosporin， 在低剂量下，我们的这个低抗原系的这个心肌细胞移植可以很顺利的恢复那个心脏功能，这是特殊的。我们现在在做心肌功能的一个画图，大家可以看到我们的这个低抗原性的它的收缩的能力恢复的不错。那我们可以，这是我们在动物实验上，我们在竹科我们用8到12个月的猪的蓝羽猪，35到40公斤，我们给它做这个心脏的手术，还有引起它的心肌梗塞，然后再给它治疗。那我们可以看到这个用这个染色可以看到这个我们把人的细胞移到猪的心肌上面染色染出来的绿色荧光然后在这个是红色荧光的红色染色，可以看到说我们的心肌细胞在猪的心肌梗塞的 model 里面可以活得很好那我可以看一下这个是我们打下去的动物模型这个是 vehicle， 那这是我们用我们这个低抗原性心肌细胞在低 cyclosporin 的剂量下它的收缩功能可以恢复得很好对不起，这个跳动好像没有办法恢复跳动。对不起啊，这没有跳动。我们刚刚是要秀我们的这个 cardiac echo 在猪的心脏细胞跳动的功能那目前我们的低抗原系的免疫干细胞，我们希望未来在癌症也可以使用。那怎么做呢？我们要把 iPSC 分化到 INK 那我们未来会再加上BiPAP 的 binding， 让它可以直接攻击患者体内的癌细胞。就是说 BiPAP 就是一边是接着我们的 INK， 一边接的是肿瘤细胞表面的一个抗原，那我们可以直接攻击 那个肿瘤细胞。那我们未来还在发展，我们希望在糖尿病的病人使用，我们可以把它 induce 到 PP cell， 然后再种在五骨的小细胞里面，再往下传哈，可以减少糖尿病。那也在一个前额失智病人，我们希望把他的 iPSC 的细胞 induce， 我把那个可瑞回来以后，种入他脑中来治疗他的前额的退化性疾病。那我们也在泡泡龙的病人，我们希望把他的皮肤的细胞，这个有缺陷细胞，用合并基因 edit 的方式，把它基因把它可瑞回来以后，再把它放大，再种植回去，把它克服他全身性的皮肤性疾病哈。好，谢谢。这是我们团队之前所得到的2个奖项，一个就是属于心肌细胞的再生的奖项，一个是有关于前额退化症、脑退化性疾病的奖项哈。那这是我们的临床试验的整个我们在培养细胞的 procedure。那我们现在在谈的是临床一起的，跟 TFDA 在谈论临床一起的临床试验。好，我们的结论是，我们的心肌细胞可以有效的改善心肌功能。那我们的 NK 也要治疗癌症。那我们神经细胞跟间质干细胞在治疗糖尿病跟这些泡泡龙的单一基因突变疾病哈。那以上是我们的结论，谢谢各位。
谢谢沈教授。下一项技术是医材领域，我们欢迎嘉义长庚医院王世宪主治医师带来的技术是腹腔镜无网片式疝气针。
大家好，我跟各位介绍腹腔镜无网片式疝气针。未来它将为整个疝气手术，那让它整个疝气手术变得更加的轻松，更加的舒适。身体上任何一个组织或者是器官离开它原来的位置，通常是有一个破洞然后呢，那这个就是构成了疝气。那我们这个腹股沟的位置刚好就在体腔的最底部，承受最大的一个重力，所以腹股沟疝气是一个最常见的疝气在台湾1年大约有3万例的疝气手术，在美国北美有80万例的疝气手术在进行那目前为止，疝气的手术呢，必须铺上人工网膜，在那个破洞的地方铺上网膜那你当然有各种不同的方式把这个网膜铺上，你可以有传统的open 的手术，那你可以有腹腔镜微创手术，那当然现在有最新的达文西手术。那每一个手术呢，这个时间大约都在1-2个小时之间，有时候甚至3个小时。那医生的这个学习的过程学习曲线呢，大约在50-60例左右。那费用呢也跟着慢慢增加但是呢，不论怎么样，一个人工网膜放在身体里边，它还是会带来一些后遗症有一些副作用。人工网膜呢，会让病人呢有一些外来物的感觉，人工网膜有可能侵蚀到周边的组织，然后可能造成感染的风险那更何况病人术后经常会这边伤口的地方会非常的肿胀，然后会疼痛相当久的一段时间，甚至造成慢性疼痛。慢性疼痛是什么概念呢？想象一个刀开完这个痛会跟着你一辈子，这个对病人跟医生来讲都是一个长久的梦魇我们怎么处理这个问题怎么解决呢？我们开创了一个腹腔镜疝气针英文叫 APERS 它是一个世界首创的一个东西有包括3个针组。那在这个针组的作用之下呢，它巧妙的地方在于说，它会闪过布满神经的组织呢，让我们的整个手术过程呢，在没有神经的这个地方呢，做手术那短短的在20分钟内完成手术。那因为我们没有碰到神经，病人术后不太痛休息一下子就可以回家了那回家以后1个礼拜呢，你可以看到病人的伤口呢，几乎要用放大镜才看得到这个时候通常我就跟病人说，你可以回家去做重训了好，我们的产品呢，制裁已经布局完成那预计明年通过510K 就可以上市我再讲清楚一点70%的疝气呢， 可以用我们的针组呢，用这样子穿针引线的方式呢，在20分钟以内，好像束口袋一样就把它绑扎起来哈。那另外还是有30%呢，你必须铺上人工网膜。那这样子的网膜呢，用我们的针组可以把它做固定。固定了以后呢，这个网膜不会跑掉，病人就不会复发哈。我们又发现说，我们现在有很多刀嘛哈，有很多刀都是用微创手术在进行，术后会有一个微创的伤口。我们的针组可以用来关闭这个微创的伤口，还有漏斗胸手术术后钢板放置以后呢，可以用来做这个钢板的固定哈。以上我们讲的呢，已经最少有1200例的概念认证哈。好，我们的竞品当然就是目前通行的人工网膜，这个在世界上有几个医材大厂的手上哈。那但是呢，我们这个是完全不同的概念，不需要铺上人工网膜哈，所以当然就没有人工网膜带来的这些后遗症哈，不会有肿胀啦，不会有疼痛，那不会有这个感染啊这些风险。但是最重要的是什么？最重要的是我们的手术时间20分钟。当别人一台疝气还在开的时候，我们已经开了快5台了哈。这个在最近各位都知道，台湾的医疗护理师，越来越缺乏，麻醉医师也缺乏，每一个医生、手术医生的手术时间都被限缩了，所以这件事情是非常重要的哈。这个市场到底有多大呢？我们从嘉义长庚，我们从整个长庚体系出发哈。事实上，长庚已经都帮我们预备好了哈。我们率先成立的全国第一个疝气医学中心哈。那整个长庚大概有3000台的一年的量能哈。我们 bottom up 算上去哈，它的整个台湾的这个市场大概可以到800万美金的一个市场哈。那当然，我们眼睛是看全世界的，看国际的。那未来呢，我们往国际去发展，这个整个单单在北美的这个市场，就到5.6亿美金的一个规模哈。那由美国，我们再进到全世界去。我们的 business model 在台湾会经过2个。我们公司的产品直接进到长庚，然后就直接在病人身上使用，这是第一个。那其他的医学中心呢，我们就透过代理商进到其他的各个医学中心建码使用。那这些代理商呢，我们其实也都找好了，都准备好了。那如果是国外呢，我们则希望用买断的方式用经销商的方式就直接代理就直接这样子。那当然在这个过程当中，如果有国外的医疗大厂那对我们的产品有兴趣，那我们也是可以直接卖掉就我刚刚讲的跟各位报告的这个市场的规模，还有我们的定价策略我们做出了这个5年的报表各位可以看到，我们预计在2028年的时候可以转亏为盈然后开始就直线上升直线冲上去那但是前面这3年我这边有框起来前面这3年我们还是需要一些资金的那这个加起来就是1.67个 million 的一个美金。好，过去2年来，我们在国家在国科会的辅导之下我们完成的法规的分析、专利的布局。那目前我们公司成立那我们甚至也开始在做人体试验。预计明年取证成功，那我们就开始上市那在这段空窗期那我们自己团队呢也准备了500万台币的一个资金先填补这段时间那刚刚我报告过我们还需要有1.67个 million 的一个资金那让我们帮助我们呢走到全世界去那这个是我们未来募资的计划那我们团队呢，我个人有1000例以上的pass 的经验。我跟各位强调这个技术学习非常简单，5例以内一定可以学得会那何东如医师呢，他是我们整个长庚体系的这个泌尿科的这个的这个总执行的一个人物所以也就是说我们在长庚的通路上是没有什么问题的我们有非常专业 的这个财务长哦，那陈玉龙博士呢，帮我们做这个整个那个业务的规划哈。那我们有法规的人员，那我们有技术长，帮我们做未来的技术的第2代的发展哈。那以上是我的报告，谢谢。
好，谢谢王医师，请回座。下项技术同样是医材领域的技术，我们欢迎国立台湾大学电机工程学系陈正维副教授带来的技术是 iCross 婴儿心脏机器人辅助手术系统。
好，各位来宾、各位嘉宾，大家早安，我是台大电机系陈正伟。那我们今天要分享的题目跟刚刚会比较不一样一点，我们是做 surgical robotics 的。首先先简单的跟大家 review 一下这个领域它未来的前景哦。那其实这个手术机器人的题材已经发酵很多年了，大家可以看到达文西在市场上的成功，以及后面还有很多后继者相继的投入在这个市场里面。那目前的 projection 是到了2030年的时候会有134 billion 的 market share。那左下角这张图，这个报告的左下角哦，它把达文西手术常常开的这个科别哦给列出来。那我们依序按照这个比例哦，可以看到在神经外科、在泌尿科、妇科以及骨科这几个重点的外科领域，达文西有相当高的市占率。但是有一个问题哦，就是有一些手术好像没有出现在这个表里面，对不对？那为什么呢？主要的原因，我大概把它整理在这个地方。首先，第一个，如果我们今天想要做小一点的、微小一点的微创手术，例如说我要在婴儿身上做手术，那我的伤口、我的器械，它的大小会比现有达文西在操作上来得更小啊。所以左边这张图我们可以看到那个达文西的 instrument 跟婴儿大小的比例哦。那这张图非常有趣哦，你看到其实如果用达文西来开婴儿的话，有点像是大炮打小鸟的感觉。那再来呢？当我们在做显微手术的时候，医生会用显微镜去放大那个操作的区域，这样他才可以看得更清楚，操作得更精准。但是当我们放大那个手术的区域的时候，医生相对的他会失去对深度、距离的感知。好，所以如果透过手术机器人来做这件事情，这个问题会更大。所以我们必须要解决这个问题，才可以把手术机器人技术应用在其他的科别里面。然后最后就是，当医生使用手术机器人做远端遥控手术的时候，不可避免的，他就失去了临场的触觉的感知啊。所以这个东西也是我们必须要克服的困难之一。那在过去的几年呢，我们与台大医院外科心脏外科黄淑健黄医师，那共同合作开发了这一套手术机器人系统。那这个系统，我们今天有在未来科技展里面展出，大家如果有空的话，待会可以移步到机器人专区，我们学生在那边会 demo 给大家看。那这台机器人呢，有点类似达文西，它一样有好几个机械手臂，这边我们放了2个机械手臂。那这个机械手臂呢，它最大的特色就是，当我的器械2个手术器械在一个微小的伤口里面做协作的时候，它那个机器人本身不会撞在一起。这件事情就是达文西做不到的，因为达文西的体积太庞大了。然后再来呢，我们也开发了这个 sensing 还有 actuation 的技术，让我的感知还有我的驱动的精准度都可以小在1个 millimeter 以下啊。这件事情也是达文西做不到的。大家都觉得手术机器人其实非常的精准，但是其实你如果仔细去看达文西的 paper， 他们的 accuracy 大概会落在1公分左右，其实还蛮可怕的。那当然做 teleoperation 不会有不会有安全性那上面的问题哦。可是如果今天我们想要进一步把手术机器人技术往自动化或半自动化推展，那这个就会变成一个非常关键的瓶颈。好，然后最后我们的技术也同时支援力回馈。OK， 好，那我们可以一项一项来看哦。首先是机构的部分，机器手臂的机构的部分。那左边这张图就是传统那个医生在做 training 的时候，所以我们机器人也可以做一模一样的事情，把那个三角形的小 pack 一个一个挪到你想要的地方去。好，那这台机器人它的自由度就跟人手一样，它有6个自由度，它可以自由的把手术器械放到医生想要放的位置去。然后再来呢，我们跟达文西不同的是，我们可以 adapt 基本上所有在腹腔镜里面使用的 surgical instrument。 如果是用达文西的话，它必须用它专用的 instrument， 那个东西价格就非常的高。但是在我们这边，我们基本上就是把现有的 instrument 装上我们的手臂就可以运作了。然后最后呢，我们可以同时做 teleoperation 远端操作，或者是做自动化，这件事情在我们的系统都是支援的，而且精准度非常的高。好，那我们系统另外一个重要的特色是，我们有办法做即时的 RGB 感知。那这个 RGB 就是平面的彩色2D 的影像。那这个 D 代表的是3维的深度图。好，那如果大家对机器人学稍微有一点概念，应该会知道，我们如果用影像来导引机器人做动作，但是那个影像是2维的，我要怎么样让机器人知道那个距离要怎么走？那答案就是我们必须要有一个深度的摄影机。但是大部分市面上可以取得的深度摄影机，它要么精度不够，要么它的 frame rate 太低，没有办法直接用在手术机器人这个领域。所以为了这件事情，我们特别想办法开发了一套 RGBD 即时的系统。那我们可以看到，左边这张 RGBD 是我们在 Phantom 上面模拟做一个夹钳的动作，那个黄色的是2个 mm 的一个小热缩套、小血管的模型。好，所以你可以看到我们的影像，深度影像可以清楚的照出2个 mm 直径的血管。那医生在做手术的时候，他只要慢慢的到达他的位置，再看一眼深度图，他就知道他的距离对不对了。那甚至我们也可以把这件事情放成3维的点云给医生参考。对，那这些都是要由我们的 RGBD 的这个影像探头才做得到的事情。好，那最后最重要的事情就是，有了刚刚这个机器人还有这个影像的回馈，对医生来讲，他要做操作，他如果失去了临场的触觉，就跟打电动玩具一样，他有时候会不小心多超过了一点，或没有 reach 到他想要的位置。所以在我们的系统里面，我们也整合了力感测以及力回馈的机制。那这个机制呢，透过一些自动化的演算法，它甚至可以产生一些 guidance 的暗示，透过力觉来帮助医生完成他的手术的动作、手术的操作。好，那左手边是我们模拟的图片，那右手边是这整套系统在手术房里面做活体实验的照片。好，那这套系统呢，目前我们是拿它来做婴儿的动脉开放导管PDA， 这是一个先天性的心脏疾病就是如果婴儿是早产，他的动脉导管还没有来得及 close， 那这个时候就必须要做 surgical intervention 把它给结扎掉。那在这个实验里面，我们用的是16天大的蓝羽猪、李宋猪。那做完这个远端的结扎手术之后呢，这个猪是可以成功存活的，代表我们的精度还有远端操作的能力是绝对可以来执行这样子精细的手术。好，那简单的结论，我们设计了一台跟达文西稍微不大一样的手术机器人，它可以做得更准然后再来它也有更好的感知的能力。那 Future Work 就是我们可以做一些自动化的演算法。以上，谢谢大家。
谢谢陈教授，请回座。下一项技术同样是医材领域的技术，我们欢迎国立阳明交通大学电子所李正仪特聘教授带来的技术是以可程式化介电泳晶片为基础的单细胞操控技术。
好，在场的各位先进大家早安。那我想我今天很高兴有这个机会呢，来跟大家分享一下全球首做的可稀释的一个单细胞操控的一个平台那因为这个平台本身基本上可以操控所以又可以携带，所以我们现阶段大概就有跟国内国外透过我们把这样的一个机台呢，直接拿到不管是业界或者是这个研究单位呢。去从事很多的这样的一个学术的这个交流甚至产业界这样的看是不是能够去创造一些新的这个在细胞生物学跟医学检测这样的一个新的这个市场商机出来那基本上呢，这样的一个机台呢，能够变成这么小其实最主要的呢，它的核心就是我手中所呈现出来这个微小的一个晶片，这个晶片本身的这个大小呢，基本上就只有1.2乘1.2毫米平方那在国内这边，我想大家都知道，国内有非常在国际上竞争力的这个 半导体的这一个制程，那我们就尝试呢，把细胞生物学里面的这个需求呢，跟国内的这个半导体去把它结合在一起。简单来讲，就是说在这个平台里头呢，基本上它大概就是2个特色，一个是我刚刚所秀给大家的一个第一批的一个晶片，那另外一个的话呢，我们再结合那个新的这个 AI， 然后把它整合到这样的一个小的这个机台上面。好，那因为这个相关的这个技术实际上也那个发表在IEEE 重要的这一个生物医学的一个期刊了哈。那我们大概就是有一些的这一个展示，基本上呢可以提供给大家来做这样的一个参考。那后面呢，我大概就会把这个平台的一些的这个特色呢透过几张我们所整理出来的这一个那个投影片呢，跟大家一起来分享。OK， 那第一个当然就是这一个呢技术，因为我们当时就已经有做国内外的这一个布局。那目前的话，大概就是台湾、日本，然后已经有通过这样的一个专利那美国这边的话，目前正在这一个 review 之中。那整个的这一个技术其实是相当的这个简单，因为第一批的这一个技术实际上已经是一个非常成熟的，可是我们的团队呢是第一次用半导体的这一个标准的一个制程，结合软体的一个方式去做这样的一个操控。那它的好处呢是可以做所谓的这一个non-invasive， 就是对这一个细胞在整个那个检测的这个过程里头呢是不会有所谓的这一个破坏性的一个影响。那透过这样的一个方式呢，对于后续的这一个细胞后续在整个不管是治疗、药物的开发等等，都可以呢扮演非常重要的这一个角色那尤其是因为这个本身实际上是使用台积电的这个制程，那我们也尽量的呢去把它操作的这个电压降低下来可以在这一个1.8伏以下或是更低，减少对这一个细胞本身的一个伤害。那这一些的话呢，我想大概就是有一些在我们的这一个chip 上面呢能够去呈现出来了那我想这个部分如果说在场的各位先进感兴趣的话呢，也可以等一下到那个隔壁我们的这一个展场这边呢去做那一个呢更深入的这个交流那基本上这边所有的呢大概都是透过那一个这些这个控的一个方式大概就可以了那我们刚刚有特别强调，就是说在整个这个操作的一个过程呢，基本上比如说以这一个右边这边的话，右边这边大概就是你可以呢去透过这一个多细胞多绕线的这个方式排出那个呢所需要的这样的一个图案。那另外一张的这个图呢，实际上你可以呢，比如说把这一个呢细胞分清完之后呢。然后在这个晶片上面呢，提供不同的这一个新的这一个开发的这个药物，然后去做一些的这一个那个测试等等。那这样子的话呢，对于未来的这个药物的这个开发，基本上也会有这一种加速的这个效果。OK 这大概是可以透过这样的一个方式去做适当的一个呈现。那我们也希望就是说这样的一个平台，你。不对于这一个实际的这个转的这个人，他不需要有非常这一个专业的这一个 ICT 这方面的一个背景那我们就开发一些的这一个操控的一个软体，让使用者可以非常的这一个方便来使用。OK 那所以呢从这个角度，基本上呢我们应该就可以呢去看到了未来的这一个市场因为现阶段跟国外的一些合作的这个厂商实际上已经开始在做所谓的这一个细胞分类跟纯化那这些对于未来的这一个细胞的这一个治疗，实际上可以呢提供非常具有竞争力的这个方案。那另外一个的话呢，就是我刚刚所提到的你可以呢在这一个呢药物开发的过程里头呢，透过这样的一个方式呢去加速这整个的那个开发的这个时程。那最后一个大概就是因为我们可以有效、快速，而且透过软体操控的这个方式，可以对于很多那个呢现有的这个医学检测提供一个更快、更精准这样的一个方案出来。 OK， 好，那这个大概也是一些的这一个了啊，我们所开发的这样的一个软体界面，所以我想基本上大概是这样的一个方式了啊。那我们还是非常这一个感谢这个那个学校的一个团队啊，那大概前后有10几个这一个学生投入到这样的一个计划，那国科会这边计划的这一个支持，然后另外实际上我在这边没有放的呢，就是说这个计划在也有国际的这个合作哈，包含京都大学那个 Sala Foundation Professor Yamada Sensei 他的这一个团队也跟我们合作，那也有那个斯坦福的这个团队，目前我们有这样的一个机台也在那边进行一些的这一个测试。那专利的这个部分，因为我们布局那个蛮多那所以也感谢这一个校友那一个专案的一个支持。以上，谢谢大家，谢谢。
谢谢李教授。接下来的技术发表将进入绿能环保与近邻科技领域。首先，让我们欢迎国立中兴大学罗景文助理教授带来的技术，应用微奈米结构提升冰泥热交换器性能。
好，各位来宾，大家好，大家早。那我是国立中兴大学机械系罗景文。那我们今天要报告这个题目呢，技术来源是来自于国科会的这个专案哈，那这个是近邻碳排的专案，只是我们是指计划3哈，应用微奈米科技来提升冰泥的热传。好，我先介绍一下冰泥哦，冰泥其实就有点像湿热冰 ，OK， 那这个系统呢，它其实可以直接的去应用在商办工厂，那我们已经有实际的去应用上了。那它其实只要建设一个 ice slurry generator 去制冰，制冰完之后除冰，然后就把冰直接打到我们的冰水主机就可以了。那这个作用能够干嘛呢？这个作用能够达到削峰填谷的效果。我可以在晚上的时候制冰，用晚上的电，花晚上的钱，在白天的时候融冰，吹凉凉的冷气。OK， 那早上7度，晚上3度，早上7块，晚上3块，你就省了4块钱。好，那我们这个团队主要的技术突破点是我们成功了建设了一套连续式的真空冰泥除冰空调系统。那真空制冰不是什么新的技术，只是它之前都是批次式的，一桶一桶的做。那我们这个团队呢，搭配了子计划1的自动控制技术，以及子计划2的散蒸技术，我们利用水的3项点来制冰，而且可以达到连续式的不中断行为，而且我们可以制作出非常好、品质非常好的冰泥。那再搭配我们这次的子计划3，利用微奈米的增强冰泥热传性能，来去达到这个加成的效果。那这个计划也后来有获得这个专利。OK， 那我们的这个量测系统呢是自己制作的。那整体来说可以量测热传，而且可以借由可视化的效果来去进行分析你的里面的冰泥的状态，不管是测试或者是上视图。那我们可以搭配我们的这个 flow meter， 可以直接的量测到冰泥的密度。那我们探讨的这个超疏水结构呢，其实事实上它就是一个奈米型的这个结构，然后在上面铺一层薄薄的疏水材料。那我们这次研究了2种表面哦，那一个是平的一般的铜管的表面，那一种是超疏水表面。那超疏水这个制作方式也非常简单，它只要经过一般的清洗，再经过搭配这个弱酸性去除有机溶剂之后，搭配碱性溶液来去蚀刻出奈米结构，最后再用这个疏水材料涂布在你的表面上，就可以形成超疏水哦，就是我们右下角的这张 contact angle 的图，水滴的呈现是一个珠状的状态，所以在表面上是非常容易滑动的。那我们的这个结果也可以呈现出这个冰晶的尺寸的量测是非常的一致的，所以我们制作出来的品质是非常的好。那这个冰晶你可以注意看它的颗粒是圆状的，它不是精致状的，所以精致状是非常容易卡在表面。那我们的技术可以控制它都是圆圆的这样子。那我们这次总共研究了3种浓度，分别是 IPF 5%、10%跟15%。那这个其实概念就是有点像浓度的概念。那右边这张图呢，是从横向的去看冰泥的流场，我们可以发现到它这个冰泥的流速，不管是在浓度5%、10%或15%，它的流速都是非常的均匀的。好，那最后讲一下我们的热传结果。我们热传结果，我们根据这张我们研究出来的结果图，虚线是只有单纯用水的情况。那灰色的这个 symbol 是我们今天做水的结果啊。那水跟虚线其实是蛮接近，大概10%的误差，验证我们的实验系统是正确的。那我们加入冰泥之后，可以提升大概8到28%的热传效果。那 但是因为冰泥其实加进去之后，我们可能会增加我们的压降，增加我们的压降。那我们也有采用了超疏水表面来去更去增加它的这个效果。那我们可以看到这个空心的结果就是我们加了超疏水表面的冰泥流场，它的热传效果可以再往上提升31%到37%。那整体而言可以提升大概到60%左右。那其实它增强机制呢，我们是参考了这3篇的这个独立研究哈，分别是这个我们减少了这个 thermal bonded layer， 然后制造了一些微 vortex， 然后还有这个冰融化所释放的潜热。那冰泥它还有一个诟病，就是说你采用冰泥之后，你的压降会变大，你可能会需要花更多的能量去推冰泥哦。那我们这边也证实了这件事情哦，就是如果你今天是用冰泥的话，它的确会提升这个压降。那我们靠着超疏水表面的应用，可以降低它的压降大概9到20%。那如此一来，我们就是可以减缓这个增强热传所带来的 penalty。OK， 那所以我就去量测一下这2个之间的综合性比较。那一般而言，我们做热传的都知道，就是你热传的增幅跟压力的增幅其实是正相关的哦。你给一份热可以带走一份的你给一份压降可以带走一份热传。那我们的结果证实的是可以带走大于一份的，可以到1.5到1.8左右。所以我们的这个技术是非常的有用的。最后我们做个总结哈，我们这个研究建设了一套这个热流系统，那它是可视化的啊。除此之外，我们有制作出非常优良的冰梨。那这个相对于单向水来说的话，我们的冰梨可以提升大概8到28%的热传。那超疏水表面的话，可以同时的增加热传，又可以降低冰泥。那采用超疏水表面的话，这个冰泥的热传可以再提升31%到37%，还可以降低压降到9到28%。OK， 好，那当然要谢谢国科会这次的这个计划，还有谢谢其他学校各位老师的参与。好，谢谢各位。
谢谢罗教授。接下来即将发表的是元智大学于俊伟博士后研究员发表的技术为次世代 PEM 电解技术至低碳臭氧与负碳滤清。
各位先进大家好，那我们今天主要是来跟各位分享，就是有关于我们是使用这个质子交换膜的电解技术来制造这个所谓的低碳的臭氧，然后包含我们还有一个副产物是我们的这个负碳氢的一个部分。那我们当然是希望将我们这些气体主要是应用在这个半导体的工业上。好，那我们的技术上我们基本上是建构在就是在这个质子交换膜的这样子的一个技术上。那这个技术呢，基本上我们将水通入之后，我们给予它的这个电。那透过我们的触尾做分解之后呢，它可以帮我们把水的这部分做一个分解。那分解开来之后呢，我们的这个氢质子会透过我们的选择性的薄膜到另外一侧产生出高纯度的一个氢气。那这个氢气透过这样子的一个系统，它基本上可以产生是5个 N 等级的这样子一个氢气。那它当然是可以使用在这个半导体的某些制程上面那当然是传统的这种 PEM 的电解它只能产生出所谓的氧气。跟这个氢气的一个部分，那当然我们的技术上，我们透过这个电极材料的一个修改那我们可以把我们的这个氧气的部分，再让它合成出所谓的这个臭氧。那在传统的这个所谓各位可以看到，就是阳极的这个材料都会使用这个大量的这个贵金属，那基本上会造成它的这个制作的成本是稍微比较高昂的一个部分。那我们在使用的部分，我们是不使用贵金属所以我们可以可以将这个成本做一个大幅度的一个下修。那我们的技术到底在半导体上我们可以供应什么那基本上我们的这个技术产出来的这个氢气那基本上它是可以达到5个 N 等级所以它是属于可以当这个电子级的一个材料去做一个电子级的气体去做使用。那另外的部分就是这个氢气因为来自于它是属于我们的副产物所以它本身是属于低碳它可以成为这个低碳的这个能源的一个来源体那第二个部分就是说，它这个氢气的部分呢，它其实可以再进入到所谓的这个制成的气体来去做一个使用。那我们装置主要供应的是这个所谓的高浓度的一个臭氧气体。那我们也知道，就是说现阶段我们的晶片越做越细微那已经进入到这个7奈米的这个先进制程的一个发展。那在它线径越来越细的情况下，传统的这种化学药剂的一个清理方式已经无法满足所以在这个部分可能就会有一些残留的一个问题存在，那会 要解决这个问题，那现阶段当然是使用大量的这个超纯水来去做一个冲洗，但是即使这样子做，我们还是无法避免说它可能会有一些残留问题所以我们就是希望用这个超高纯度的这个臭氧来去做一个清洗的一个部分。那当然，因为臭氧它本身的一个特性就是它在室温下30分钟内它会有一个就是自分解这样的一个部分变成一个氧气，然后去做逸散。所以在这样子的一个部分的话，我们就可以避免我们的这个在清洗过程当中会有这个药剂残留在这个所谓的这个 wafer 表面这样子的一个问题。那另外一个部分就是说，因为它的这个自分解特性它对于这个环境的友善性是非常好的那当然，我们从研究中也可以看到，就是说，如果在这个制程当中，我们导入了臭氧来去做一个清洗，它基本上可以大幅度的去降低所谓的化学药剂的一个使用量。那当然，相对来说，就是它可以大幅降低你的这个制程的一个成本所以我们的技术跟以往不同，就是以往的氢气跟臭氧它都是属于个别制造。那我们现在的技术就是透过同一个装置，我们从一侧可以产生出我们要的高纯度的一个臭氧，然后另外一侧就是产生我们可以使用的这个高纯度的一个氢气的一个部分。那表上我们上面也可以看到就是传统的这个臭氧制作方式它非常麻烦，它是要用2阶段式的一个生产从空气中先纯化出氧气之后，氧气再做高压放电，然后再产生出这样这个高浓度再产生出这个臭氧的一个气体的一个部分。那这个臭氧的气体它基本上的浓度一般的一个一般的这个发生器它大概是低于10个微%那我们团队呢是直接透过水1阶段式的一个转换，将水直接就是电解产生出这个高浓度的一个臭氧。那我们的臭氧气体它的这个浓度呢，其实可以达到16个微%那当然我们在小型化的设计上已经有超过20个微%这样子的一个能力那另外一个部分，我们另外一端就是产生出刚刚提到的这个5N 等级的一个氢气所以这个臭氧跟氢气它同样都可以再进入我们的制程中去做一个使用那在我们的这个关键技术就是我们内部的这个复合型的这个触媒奈米的一个触媒的一个部分。那这个触媒它本身因为它要产生高浓度的臭氧，所以它对于这个抗氧化的一个特性非常讲究所以我们可以有效延长我们整个技术操作的这个能力跟产品的这个寿命。那另外就是在我们接触到臭氧这个强氧化环境的这个材料呢，我们的表面也有涂覆所谓的这个抗蚀层。那这个抗蚀层的一个部分就是避免我们材料在这个强氧化环境下有一个所谓的腐蚀的一个现象所以我们透过这2个技术的一个加持，让我们的这个装置在产生高浓度臭氧的情况下，也可以维持它的一个寿命。那我们目前已经跟半导体知名的这个设备商做一个整合。那我们优先导入的项目是在这个半导体废液的处理的一个部分。那所处理的这个废液呢，它的浓度其实是高达 COD 是高达这个12000到14000每 liter 这样子的一个值。那我们透过我们的这样子这个技术，基本上我们可以在10小时内跟它的这个高级氧化法技术做整合，然后把这个高 COD 的原液废液的部分快速的做一个降解，达到一个可排放的一个目标。那当然在厂商的验证部分，它也透过长时间的观测去观测我们整体对于这个臭氧输出能力的一个稳定度那基本上我们目前的这个模组在实际场内运作已经超过了1800个小时以上那它在浓度的监测上一直都可以保持在190个 ppm 以上的一个稳定输出那画面的最右侧的部分就是我们的这个臭氧的一个产生的一个模组那它一侧是可以产生出高浓度的臭氧，一侧就是高纯度的一个氢气的部分。那它实际大小的话，大约就是11乘11乘11这样子的一个立方体的一个大小。所以我们的技术跟传统的这个空气放电法相比，就是一般的这个制程相比，它的优势在于什么？它的优势在于说我们大幅度的简化整个制程，我们不需要2阶段式的转化，我们从1段式从水直接变成。第二个部分是我们提供更高浓度的一个臭氧的一个数值。此外的部分就是我们在装置产生的氢气，它其实可以拿来做不管是能源应用，或是再回到传统的制程上的一个部分，它都可以去做一个大幅度的一个使用。那未来跟绿能结合的话，它的这个碳排放量可以再往下修相对是更低、更环保的一个部分。那当然，我们跟同级竞品相比，那同级竞品相比，它的这个产生每克这个臭氧的一个能耗，其实还是相对于我们高了许多我们大概是可以节省至少15%这样子的一个能耗。那另外，我们针对我们的这个材料的部分，还有我们的客制化的部分，都有提供特别的一些特殊的服务。那同时，我们有布局其他的一个专利 在这个其他的这个产业应用的一个部分。那在专利的部分，在技术专利的部分，我们大概目前排名在全球第8位。那当然前面有一些实验这些大公司，那我们当然持续在提升我们这个技术的一个竞争力。那最后的一个部分就是说，我们目前在 milestone 的话，我们目前已经销售8个模组到业界去。那接下来就是我们在明年度，我们会将我们的整体产量提升到200克这样子一个臭氧产生的一个浓度。那透过这种方式呢，我们可以媒合这个所谓的业界的一个需求这样子。OK， 好，不好意思。好，那我最后做一个总结哦。我们的技术不止可以用在这个所谓的绿色半导体的部分，我们同时也在今年度会开始进行所谓的不管是食品工业或是有机农业的方面的一个这样子的一个产业的一个布局。所以我们的技术的总结就是我们透过一滴水，然后来去产生我们所需要的这个高纯度的一个臭氧跟氢气的一个部分。谢谢大家。
谢谢于博士，请回座。今天最后一位发表的是国立成功大学陈志宏助理研究员，发表的技术为智慧型移动式水体温室气体监测无人平台。
各位先进好，各位来宾，大家午安。那今天呢，由我来代表我们团队来跟大家分享我们就是在今天的就是革新的技术。那我们呢，其实是一个感谢我们国科会。那产学合作计划呢，跟我们中信造船集团，还有我们盼成技术公司，那基本上呢，其实我们在近邻科技这部分的话，就是所谓工欲善其事，必先利其器的部分。所以我们要达到近邻这个目标呢，首先要知道说，我们实际上碳排了多少，我们碳排量测的东西有没有具代表性。所以呢，我们才希望可以就是把这部分的技术呢做 upgrade。整合去搭配我们移动式的这样的就是智慧无人船，那去做整个全面的就是水域调查，然后可以得到我们就是更精确的我们实际碳排的情形哦。好，那所以说呢，就是其实呢，我们今天要做的就是做碳排这部分的技术的量测。谢谢。那包括说呢，就是其实水面上我们可能会看到它可能是会二氧化碳可能出来，也可能会进去，甲烷可能出来可能会进去。我们要真正知道说，它上台下来这个 flux 到底是多少，我们希望可以做这部分的量测。那这部分呢，其实也都是既有的一些技术啦。那我们其实是结合我们的就是团队所研发的模组化的多功能的智慧无人船，那结合它带着它一起走，我们一边去做这部分的调查。那我们这个无人船呢，其实是老师对我的一个就是鼓励。我们平常去采样的时候，你看我每年越来越长大一点，那划那个胶筏，哇，越来越辛苦，然后可能水一直不断渗进去，很危险。所以呢，我们就希望说，我们有没有办法呢，用无人船的方式帮助我们去做采样，去做水面的调查，去做水质调查，去做生态的调查。那所以我们才会有这样的一个就是计划产生。那我们就是也因此呢，就是做了很多不同模组的开发，那去满足各个部分的需求。那所谓的模组化是什么意思呢？就是其实今天我们是做技术的整合，所以今天你如果需要什么部分，那我们就帮你去做，就是这部分的就是就是把它 integrate 在上面。那我们的船的话呢，基本上我们有做很多测试，那有很大可以站2个我的船，那也有像我们在展区部分这样小船，那还是可以站1个我，那可能会歪一点，对。那其实我们都可以有很大的承载空间，那就可以去承载我们不同的模组。那其实这个船的话呢，我们就是也去让它，包括说你可以让它去做定点的巡弋，那或者说让它像那个我们扫地机器人一样，让它规定在一个范围，它自己去找。那碰壁子的时候，不要碰到，那我们就赶快避开。那这样帮我们去做整个断面的扫描，知道说整个水质啊，或者是我们空气品质的这些情形。那我们也可以搭配我们的就是我们的 camera， 那了解说，我们现在实际上呢，就是可能这边有什么生态，有什么鸟类或者什么鱼类。那我们呢也有去搭配就是 AI 的影像辨识的功能，让我们知道说，这上面是不是有一些我们有所谓的藻华，或者我们一些有毒的、有臭味的藻长在上面。那我们是不是需要去做一些必要的处理哦？那还有就是，就是我个人的痛啊，我需要做水质的采样。那其实呢，这些东西在国外其实香港、新加坡，可能很多地方美国也都有做部分的技术的开发，但只有我们呢是 有这么多功能都可以去执行，而且尤其是水质采样，我们可以采很大的量体，而且我们可以采不同的深度这个部分。那我们也有去搭配做底床量测，就可以知道说，到底我们现在这底下有没有淤积东西啊，有没有什么东西在里面？这样我们可以去做很全面性的调查哦。再搭配上我们的就是碳排这部分量测，我们就可以搭配水质，知道说，为什么这边会有热点产生？我要什么方法才可以去改善它？如何让我们的碳排可以去降低它？那所以说我们就是跳过我们所谓的桎梏，所以其实传统我们在做碳排怎么做呢？像这样子，大家看到左边这边是我们的澄清湖，大家如果早上呢从澄清湖开始走，有心用走的话呢，走到后面后门大概就下午4点了，就哭了要赶快找计程车出去。所以湖基本上呢，水库湖区非常的大。那通常呢，我们去做这种我们的就是所谓的碳排的量测呢，是像这样我们有一个罩子，那我们就只能有卡楼的地方放在岸边，放在桥边，然后就是等它就是量测稳定之后，然后我们收完 data， 然后再走，再到下一个点。所以其实我们那个量测点位非常的限制，而且你就可能中间你就测不到。为了改善这个情形呢，所以我们才希望说，我们有没有办法改变掉我们既有这种传统这样静态的这样的量测方式，用船带着走，让它可以到我们每个地方我目标点位上面去做这些的进行。那不要小看这个东西，现在各个业界是已经在做碳排的调查了嘛。那但是其实我们自然环境当中碳排的量也不容小觑。所以一定要做这些整体的整合，然后我们真的才可以知道说，那我们未来怎么样才可以有效让我们到未来目标，可以得到我们的近邻的这部分的目标哦。好，好，那所以说这就是我们就是其中一个测试的船体，大家可以看到，所以我们其实就是有在各个不同，像我们可能自己校区的湖区啊，或我们可能到我们就是一些人工湖区啊，或是一些湖泊，我们都去进行就是实际的测试哦。那所以说我们其实呢，就只要船带着我们的舱体，然后它就可以其实走。那相较于我们之前一个点可能大概要30分钟到1个小时，这个东西呢，它到一个定点停5分钟，平衡了，那我们就可以到下一个点。所以就是在这样的即时动态之下呢，得到这些 data 之后呢，我们就可以去算出每个点位的碳排。那所以就是整体看像这样，我们就可以就是设计他想要走的路径，在某些地方停下来，大概5分钟左右，那就是我们有持续的再去做就是通量的量测。那其实就可以大家知道说，我们整体的就是断面呢，在什么地方是有一些热点的产生，那我们再去搭配其他水，知道说到底为什么会这样子，那我们就可以一个是当然知道说整体平衡具代表性的数值哦，另外是知道说那热点产生的地方我们怎么去改善它。那所以说，其实我们这一个就是这个计划的这个就是船体呢，除了做这个部分的碳排的量测之外呢，其实就像我们刚刚说的，其实我们有做很多就是像采样这部分的东西。那这部分的话，我们其实目前已经完成技转了，就是也有在就是翻手这个船的部分。那当然我们不是设备制造商，我们是技术服务商哦，所以其实是你需要什么东西，我们都可以帮忙。对，那时候我们其实有整合我们的，就是一定要结合我们的就是 IoT 的技术。利用我们知道即时的点位在什么地方，它时间是什么地方，它的水质、它的空气品质、它的碳排是如何，我们才可以知道它整体的就是情形。那左边这是我们学生也有做出来，就是其实呢，我们就可以用 YOLO 方式，让 AI 这样去辨识说，现在有浮藻、有脏会产生臭味、产生有毒的藻类过去，那我们看它面积有多大，去进行说我们是不是需要做适当的一些就是改善或者去除藻动作。那以上是我们的就是这部分的报告。那欢迎大家到我们展区去实际看我们的船，谢谢大家。
谢谢陈研究员，请回座。我们再次掌声，谢谢8位老师精彩的发表，相信大家也获得满满的知识量能。紧接着我们要进入的是媒合时间，我们会先请工作人员引导老师们进入第1轮预约媒合的企业伙伴们至媒合桌。其他安排于第2及第3媒轮的企业伙伴们，可以在中间区先稍作休息。我们先为事先报名的企业朋友们安排媒合场次。若您听完上述的技术后，想要深入了解，可以先到舞台区询问工作人员，我们将视情况做安排。谢谢。
Ladies and gentlemen, welcome to the Future Tech Pavilion FuTech. FuTech is co-organized by the National Science and Technology Council and other relevant ministries. This year, FuTech is themed AI cross-disciplinary applications and innovative breakthroughs, showcasing cutting-edge research achievements from various fields both domestically and internationally, creating the most anticipated science and technology event of the year. 国科会吴主委，还有运动部黄启煌次长、中研院的陈君厚秘书长、卫福部的刘明勋技监，还有教育部的徐正邦副司长，以及呢我们现场的贵宾、媒体朋友们，大家午安，大家好。欢迎各位莅临由国科会携手中研院、教育部、卫福部及运动部打造的未来科技馆。那么今年呢，我们以 AI 跨域应用、创新突破为主题，汇集了海内外各领域前瞻科研的成果，打造了全年度最让人期待的科技盛会。And today we are very delighted to welcome distinguished international guests to this grand event. And please allow me to introduce them and give them a big round of applause. First, our speakers for today's Smart Robotics Forum. Let's give a round of applause to welcome Professor Tommy Asford from the Institute for Anthropometrics and Robotics for Koshiro at Institute of Technology. Welcome, Professor. And next, let's welcome Professor Atsuo Takanishi from Department of Modern Mechanical Engineering and Humanoid Robotics Institute at Waseda University. Welcome. Welcome, Dr. Stan Birchfield from NVIDIA. Welcome. Next, let's welcome Professor Karen Liu from Department of Computer Science at Stanford University. Welcome. Besides our speakers, we also have friends from overseas joining us. So if you are here, please stand up and wave to everyone. Once again, thank you for coming. Please give them a warm applause. Thank you. And next, we would like to invite our esteemed leader, Minister Chen Wen-Wu, to the stage for a few words. 让我们掌声欢迎国科会的吴成文主委上台为我们致辞。欢迎主委。
Good afternoon, all the distinguished guests, ladies and gentlemen. It's really my honor and privilege to be here to welcome you to this very important event, the opening of the FuTech Pavilion. And I would like to thank Professor Yue Wenhong, the Director General of the Engineering Division for National Science and Technology Council, for organizing a very important forum for smart robotics this afternoon. And for this pavilion, I would also like to thank the partners of National Science and Technology Council, including the Academia Sinica and the Ministry of Education and Ministry of Health and Welfare and Ministry of Sport. So you can see the demonstrations, the booths from all these partners all gathering here. It's very important, showing very important research results which can be realized and utilized for the industries and all sectors of the society. And I would also like to thank our distinguished speakers, including Professor Takanishi from Waseda University, and Professor Liu from Stanford University, and Dr. Birchfield from NVIDIA, and Professor Fu from National Taiwan University, and also Professor Ashford from Karlsruhe Institute of Technology. Thank you very much for joining us today. And I think all the audience gathering here are waiting for your very distinguished speech later on for the important forum of smart robotics. On behalf of the Executive Yuan of Taiwan, I would like to let our guests today to know that our government has formally approved a very important national program for smart robotics. And the program will be conducted by several ministries and councils in our government, not just National Science and Technology Council, but also Ministry of Economic Affairs, and Ministry of Digital Affairs, and Ministry of Health and Welfare, and Ministry of Agriculture, and so on, so many education as well. So many ministries joining together for the benefit of the society, of the people, to develop industries that can help serve people for the future. So the emphasis of the Smart Robotics program for our country will be focused on service robotics. Service robotics for all kinds of services that human men, I mean the humanity, for all kinds of humanity needs to serve all people. For service robotics, we emphasize not the original robotics industry, which is for manufacturing, but we emphasize AI and how to transfer human knowledge, human intelligence to the machine, and then can deal with all kinds of needs that can serve people. For even disaster prevention and recovery, which we have just encountered in Hualien the past few weeks. And for saving lives, for helping people to prevent even traffic accidents, to serve very dangerous works that originally done by human beings, but it's too dangerous, so that we can use machine to do the jobs. All kinds of needs for the society is the main purpose for the National Robotics Program. So we would like to emphasize very innovative AI-enabled applications and systems and services to help human beings. So for that purpose, we are integrating all different expertise to help come up with systems, not just components. So in Taiwan, in the past, we're focusing on the manufacturing side, ODMs and OEMs industries, EMS industries. However, in the future, based on the existing hardware manufacturing expertise that we have today, we would like to invite international collaboration partners so that we can develop smart systems that can help people, as I mentioned. And for that purpose, we need to collaborate with so many different partners from all over the world. That is why we have this forum in the afternoon, this afternoon. And we also are showing different research and technology, scientific research and technology development results in this event in the next few days. We also invite everybody to take a look at them, because that shows the results from different ministries and councils. They invested in science and technology in the past few years and showing the result here. So we also invite our international visitors here to take a look to see how Taiwan can collaborate with you together to make the world better in the future. So once again, I would like to thank everybody to join us today. And I hope that for all the visitors today here, you have a very wonderful day and fruitful event in the next couple of hours, listening to the speeches of our distinguished speakers here. And please enjoy the show. And I hope everybody can have something that you can take away to make Taiwan and the entire world better in the future. Thank you very much.
Thank you, Minister Wu, for the inspiring remarks. Please have your seat. 感谢主委的致辞，请主委先回座。Today, we are very delighted to have our distinguished guests from abroad and from various sectors join us to witness the pioneering technological outcomes at the Future Tech Pavilion. And next, we would like to invite our guests to the stage for a group photo in the following order. 我们今天现场有来自许多远道而来的朋友参与，那么难得的机会呢，有产官学研界聚集在未来科技馆。接下来呢，我们要先来进行今天的大合影。首先呢，让我们要邀请到国科会吴成文主委，继续要邀请国科会苏正刚副主委，接着要邀请科技办张正豪执行秘书。继续要邀请中研院陈君厚秘书长，继续要邀请卫福部刘明勋技监，接着要邀请教育部徐正邦副司长。And next, we would like to invite our distinguished forum guest. Let's welcome Professor Tommy Asfor. Welcome. And Professor Atsuo Takanishi. Welcome Dr. Stan Birchfield and Professor Karen Liu and Professor Li Chenfu 以及国科会工程处的洪月文处长。好，我们请各位贵宾看向正中间挥手的这台相机 ，Please look towards the center camera. And one more photo, maybe we can make a thumb up gesture， 比一个大大的赞，给我们的未来科技馆。好，我们摄影师 OK 吗？好，接下来呢，我们邀请第二阶段的合影贵宾上台。首先欢迎产学处林德生处长，竹科管理局胡世明局长，中科管理局许茂兴局长，南科管理局郑秀荣局长，前瞻处蔡妙慈处长，资讯处周子元处长，自然处赖明志处长，人文处黄俊如处长，科国处李旺龙处长，生科处涂君怡副处长，国家太空中心吴宗信主任，以及国家灾害防救科技中心陈宏宇主任，还有国家同步辐射研究中心徐家宏主任。好，我们要再次邀请贵宾看向正中间挥手的这台相机 ，Please look toward the center camera. 好，我们一样第二张比一个大大的赞 ，Please make a thumb up gesture to the camera. And one more, please look your left side this camera. 好，我们还有媒体朋友们需要捕捉的吗？Your right side. 好 ，OK, please look at the center again. 好，我们现场摄影师都 OK 了吗？那我们再次的感谢我们台上所有的贵宾。Once again, thank you for our distinguished guests. Please have your seats. 好，我们再次感谢今天与会的长官贵宾们的莅临。紧接着呢，我们要进行的就是现场来宾们呢非常期待哦，我们的智慧机器人论坛。我们的开幕论坛活动呢将聚焦在智慧机器人发展趋势。那么第一场主题演讲呢，我们非常的荣幸哦，邀请到人形机器人领域的国际权威。那么他所领导的团队呢，开发出了可以在真实环境中与人协作的人形机器人。今天呢，将为我们带来的主题是人形机器人迈向通用型智慧的未来。Now we proceed to today's opening forum, and today's event focuses on trends in intelligent robotics. So for our first keynote, we're honored to invite an international authority in humanoid robotics, Professor Tommy Asfor. Let's give a word of applause to welcome Professor Tommy Asfor.
Yeah, good afternoon, everybody. It's an honor and pleasure for me to be here. Thanks a lot for the National Science and Technology Council for inviting me and for giving me this opportunity to learn about Taiwan, about technology in Taiwan, about the motivation of young people working on smart robots in Taiwan here, and for the REACH program, what the organizers put together to give us an idea about robotics and AI research here in Taiwan. So in the next 20 minutes, I will give you a brief overview about why I think humanoids robotics is so important for our society and for our economy. As you know, robotics is everywhere. Robotics is changing the way how we work and how we live. And if you see here in these examples, robotics in production, in exploration, in construction, agriculture, in medicine. But if you look at these systems, every system has been developed in order to perform a task in a perfect way. A robot for production cannot do agriculture tasks. A robot for logistics cannot do medical robotics tasks. And this is what we would like to change with humanoid robotics. Humanoid robotics are versatile machines. This means these are machines which are able to perform a wide variety of tasks. And one day, any task what a human can do and maybe better. And the goal of our research is actually to understand the versatility of the human body and the motion intelligence of the human body. Why are we as humans so performant and can do so many things with the same embodiment, and why we are still not able actually to build technical systems in form of humanoid robots which can do the same. So we're interested in building general purpose machines which can perform any task what a human can do in order to improve and to contribute to a better quality of life of humans. And in the last year, I added the last item point on this slide, which I have been using in the last 25 years. Humanoid robotics is a multi-trillion market. Projections tell us that the market of humanoid robotics in 2035-40 will be as big as the market of automotive. What we are doing here, I have been working in this field since 25 years. These are the humanoid robots we developed at the Karlsruhe Institute of Technology in Germany. And in order to provide help and longer self-determined life for people at home. So you see here our labs, a kitchen environment where the robot should help anybody, any person in daily activities, provide versatile and personal assistance for humans at homes, but also for caregivers, for example, at nursing homes, hospitals, retirement homes. I will not go too much into the details of the research questions, but I would like to show you some examples of the work we are doing. So you see here a humanoid robot performing tasks in a kitchen environment, like loading the dishwasher, cleaning the table, or a humanoid robot helping a human to prepare dinner for 2 people, as you see on the right side, where the challenge is to map this natural language instruction, Amma, please help me to prepare dinner for 2 people, into motor actions. To have a robot which has an understanding about its own abilities, about the tasks, what it can perform, and the task which should be done by the human, for example. Since the robot cannot cut the salad, the human should cut the salad, but the robot can wipe the table, can pour the oil, and so on. And recently, we arrived at version 7 of our humanoid robots here. And the goal of this Amma Robot 7, the 7th generation, is to provide assistance for caregivers in retirement homes. So where I believe, in particular in Europe and in Germany, this is a very severe problem and labor shortage in the area of healthcare. And therefore, I believe here that humanoid robotics can provide a solution, or can provide a sustainable solution for these societal challenges. So it's not only about building these systems, about the mechatronics of the systems. You see here additional cognitive abilities of the robot, or sensory motor abilities of the robot. Robots at home should be able to deal with any object, to manipulate any object, anytime and anywhere. And you see here the abilities of the robot to handle deformable objects, but also to recognize the intention of the human in the context of handover tasks here, as you see here in these videos. It is not only about developing the hardware and the operating system behind it, which is really challenging and which we have to master in this area, but it is about building the architectures behind these hardware, behind these machines, which allow us to understand natural language, which allow us to understand situations based on visual information, and to map instructions like help me to prepare dinner for 2 people into motor commands. And we believe here in this context that these architectures should be memory-centered, and that the memory system in the human body or in the human brain is very crucial and very important. And this is why we started implementing a memory system for our cognitive architecture, in particular implementing a deep episodic memory with deep neural networks, which allow us to encode the experience of the robot and to recall this experience in a very efficient way, in order, for example, to verbalize to humans something about the past of the robot. I'm not going too much into the details, but this is how maybe this architecture works. The robot would collect everything what it perceives, the objects it perceives, the names of the objects, when it perceives or detects an object, how it grasps an object, how it manipulates it, where to place it.
Can you please tidy up while I'm away?
You see here an example. I will be away for a few minutes. Can you please tidy up? And the robot knows how to perform this task because it has plans which we encoded, for example, which was learned by the robot. And then the robot stores all camera images, the information about the objects we grasped, and so on, in order to be able to answer questions like, did you see the red cup? Yes, I last saw it on the table 10 minutes ago. Sorry. You see here how this episodic memory is built, and now Leonard is back.
Tell me what you did, please.
I moved a multivitamin juice to the countertop.
How long did it take to grasp the green cup today in the afternoon?
It took about 1 minute.
Tell me which object you moved to the countertop yesterday at 2 p.m.
I moved the red cup.
When did you last see the red cup?
I saw it on December 9th at 14:56.
So this is a very simple example, and this is what we expect actually from robots which should act or should help us at home to be able to answer these questions. If we look into the data, what we need in order to build these models, our robot generates about 350 gigabytes per hour. This means about 3.1 petabyte per year. Of course, we are not using only the raw data, but latent representations of the data, so representations in smaller dimensional spaces. But though also in these spaces the data remains significant, and this is why we are investigating how mechanisms of forgetting what we know in humans can be implemented in order to build episodic memories for robots which are as efficient, as performant, maybe at some point, as human memory systems. So the next example for humanoids, and humanoids are general purpose machines, is actually to help humans in 3D jobs, or actually to replace humans in 3D jobs, in difficult, dangerous, and dirty jobs. And you see here some examples with the 6th generation of our robot, where on the one hand, the clicker is, on the one hand, the robot is able to support or to assist a technician in repair and maintenance tasks. The robot is able to recognize when a human is in need of help based on the task information and based on the interpretation of the current situation. For example, all these tasks are tasks which require 2 people, as you see here, like lowering the guard, like setting up the ladder for the expert technician in order to inspect the conveyor belt from the top, or like placing the cart here at the right position with the tools which are needed for maintenance and repair tasks. Another example of dangerous jobs is decontamination of nuclear plants. And you see here how these decontamination tasks are done these days, where a human has to pick up objects in a box to clean them and to place them in another box. And we would like to remove this human from this environment. Yeah. And you see here how our robots are able to grasp and to manipulate difficult objects. This is about grasping of unknown objects in cluttered environments, and where the robots are also able to recognize failures and to recover from failures. I have to hurry up. The second part, what I am going to talk about, is how our robots learn from human observation. And since I'm running out of time and people are giving me signs from the back that I have to stop in 1 minute or 2 minutes, I will skip many of these exciting things where we collect data about how humans perform tasks, highly accurate data, and data about the motion of the human, but the motion of the objects, and where we can, with machine learning methods, segment these human demonstrations in elementary actions, which we call movement primitives, which can be used in order to implement complex tasks like prepare the dough, for example, or like cleaning the table. Let me skip this, how we learn actually these sparse representations of manipulation tasks based on visual information. Yeah, you see here, for example, the pouring task can be represented by very few key points of the demonstrations, which can be used in order to generalize to pouring in different cups and from different containers. You see here how this can be done also with very few number of demonstrations. So only 6 to 8 examples are needed in order to have the robot learning these bimanual coordinated or tightly coupled or loosely coupled manipulation tasks. Humanoid robots made progress, and we see a lot of new systems these days. The whole thing started at the Waseda University with the Wabot 1 humanoid robot. And I need the next slide. And the question is not actually whether humanoids robots will be part of the society, but it's about the when. And we have, I see, 4 undeniable forces. The progress we are experiencing in AI, that we are able to manufacture these robots, so mass production is happening now, what Tesla, Figa, Unitree are doing. Aging population and labor shortage, there is no other alternative for a solution. And the form factor wins. So our entire infrastructure is built for humanoid robots. And I can tell you, that some people in the room might doubt now and think what's Tamim telling me, but let me give you a few examples. 95, people said internet is a fake. Nobody needs a smartphone in 27. AI cannot understand language, 21. And today, humanoids will not work. And you see here that actually the history is on my side. The history is on my side, and the data, they are always wrong. Yeah, we had all these things. So the next revolution is the fusion of humanoid robotics and AI. And with that, I have to stop here. Thank you for your attention.
Thank you, Professor Esper, for your wonderful speech. Thank you. Please have your seat. And for our second keynote, we'll present humanoid robotics research and its application. We are honored to invite Professor Atsuo Takanishi. Let's give a warm round of applause for Professor Takanishi.
Hello. My name is Atsuo Takanishi from Waseda University, Japan. And okay, how can I fast forward? Okay, first, she's from Taiwan. She's my postdoc, a very good collaborator in my lab, doing a research on human robot like this, musical robots for long years. So this time, she even helped me a lot. And she's also a PhD student. She's Japanese, and she's making a sort of pitching robot. So you can see the video. I hope it works. Like this, very fast. Have you ever seen this before? You know, in this case, the robot is not only using actuator, but also using a spring and its mass. So it's a sort of human how to perform the energy efficient motion. This is very, very important, I believe. And she's Guzishi, she's a Chinese, and she also, he helps me a lot about doing a research on not only human, but also exoskeleton or leg prostheses, intelligent ones. And by the way, he is the first guy who started human research in history. Professor Ichiro Kato, my advisor. So unfortunately, he died in 1994, but he developed many types of humanoid. But these two robots are very famous. Robot 1 stands for Waseda Robot number 1, and the second Waseda Robot number 2. The first one was built in 1973. That time, the speed is very slow. One step, 45 seconds or even 1 minute. And the step length is only 10 centimeters. But at that time, this is the first time in history the robot walked by itself. The second one is not working, but playing a keyboard like this by reading a musical score about 1 meter away from the robot head. Okay, why human robot? Professor Kato told me that making a human robot is knowing a human self from the viewpoint of engineering. This is a very important viewpoint. That's why we have been making human robots for long years. And the second one is robotics, one of the social technology based on the human model. So after this, so we have a lot of models about the human self. So our design methodology can be based on that model in terms of engineering, I believe. So the second one is the making of a human robot is a sort of grand challenge. So when I was an elementary school kid, so I watched television, the American astronauts standing on the surface of the moon. That's a big shock to me. So after that, I more entered to science and technology. And after that, I made a lot of different types of human robot like this. Okay, this is Wabian 2. But anyway, this robot was built about 20 years ago. But you can see the robot has a special purpose mechanism. Nowadays, many robots are using that configuration. But at that time, no robot other than this has such kind of DOF configuration. And also, the mass distribution and the length of the limb system are almost same as human anatomy. So I still this robot is the most human-like humanoid robot in the world. And you can see that the robot, I hope. Okay, this robot can fully extend the knee while walking by using the pelvis motion. This is the same as how human is walking. So extend the knee is energy efficient walking than the robot like this. And also this robot can walk outside like this. Very smooth. And the important point about human science in terms of engineering is this. So human has two peaks while walking. The floor reaction force in the vertical direction. So other apes, chimpanzee or gorilla, has only one peak. So this is a big difference between human and the other type of apes. But for example, the Wabian 2 has really two peaks, like humans, while Wabian walk like this, like Ashimo's walking or something, always bending the knee. So this is a big difference. So by humanoid, we can confirm how human is moving. And also we make the foot more smaller than like human, like this. And also human robot can be used as a dummy robot. So in this case, at that time, Hitachi was developing a sort of a system. So in the end of the stage, they want to use apply to human, but still they are afraid of some injury. So they ask us to use our humanoid robot in order to replace the human with the human robot. And also human robot has so many sensors. So you can easily obtain many data if something happens, fall down or even falls walking. And also my university has a human science department. We also collaborated with them. We first measure the human motion. He's a handicap, and one half of the body doesn't move, but we try to move the data to human robot like this. And also, Okay. Oops. Okay, anyway, the society needs to change the law. This is very important in order to accept those high technology to human society. So we especially applied to the government, change the traffic law to allow a humanoid to walk or run in the public road like this. We did in the Fukuoka prefecture. By the way, Fukuoka is where I was born. Okay. Okay, we also collaborated with the European collaborator like this, Professor Paolo Dario, Alan Bertos, and many other research groups. And our technology also, not only within university, but also to distribute to companies like, not only companies, but also other governmental organizations, METI and TEMSAC, and even Sony. We collaborated and we give them licenses. And also now, like Minister Wu mentioned about disaster. This is the same situation in Japan. So from the 2015, we did a sort of collaboration research within Japan. And this is one of the research laboratories alumni, Professor Hashimoto. Now he's a full professor of Waseda too. So he made this kind of robot because he developed many human robots before. Now he is trying to make a disaster robot like this. And this is a sort of armor in order to protect the robot itself. And this is the most important part, the actuator. So we collaborated with Mitsubishi Heavy. They supplied us a lot of know-how how to make actuator. So at that time, we had a sort of small line in university, and we developed many different types of actuator like this. And just 2 weeks ago, we press released the new organization called Kyoha. So because there are many good companies located in Kyoto, so the companies organized the new organization to really develop useful humanoid. And at that time, there are several industry. This is totally industry-driven project. And now many companies are asking us to join. And very sorry, only in Japanese. I don't have time to translate to English. But like this, many parts of the robot can be supplied by those Japanese companies. And one of the most important applications is disaster. Because Japan is maybe the top in the world, having many different types of disasters. So the first thing that we have to concentrate on is this. By the way, like a pitching robot, this robot is running like this, using a spring mechanism. So this is this kind of motion can be energy efficiently done by using this kind of mechanism. And also my young colleague, Professor Otani, and also one of my young alumni developed this kind of two-leg chair. Because in the real environment, wheelchair cannot be used sometimes, like steps over here. So if the chair has this kind of two-leg mechanism, so you can go up, down the staircases like this. And this is also collaborated with the Japanese company Tenza. Okay, and it's something like 20 years ago. But we moved this robot to Los Angeles. And there are many people get on that robot. He was a mayor of Los Angeles. I don't know if he's continuing the mayor. Maybe in the US it's impossible. And okay, this is my collaborator in research, musical robot. I hope this robot can, okay. You can enjoy the robot playing the flute. This robot has 2 lungs, like humans. So this robot needs to breathe in order to continue the play. And you can see the lip, depending on the tone, the lip shape changes in order to make optimal sound. So that methodology was learned from a professional flutist. Okay, this is a saxophonist robot. Okay. By the way, this research is done by a German student. Now he's because he's a semi-professional of the saxophone player, so he made this robot. Okay, next robot is speech production robot. This is a collaboration with NTT, you know, Japanese telephone company. So they want to have this kind of robot in order to do research on human, how human is producing speech. I hope you can see, this is Japanese, Bawel, Aoi, Ue, O. This is volume up, please. Okay, if you access to my lab webpage, you can listen to the different speech by this robot. But anyway, speaking of human speech was very, very tough. So you can understand how human is, very greatly produce many types of motion like this, performance. You need to be air tightness. This is very important. So this is IUL, the other types of speech production. So very, very hard to listen, but we just do that. And this is not a speech. This is a sort of drinking. Okay, this is a more, mental related human robot. Okay. The important thing is equations of emotion. So we need sort of equations in order to control robot precisely. But we believe that there should be a sort of equation for emotion. So this is our idea. After that, the robot performs like this. In the beginning, the robot sees the rainbow. Robot expressed the happiness, but the robot has many different sensors on the body. If you hit, the robot reacts almost real time. And the robot has 2 microphones in the middle of the ear. So robot can localize the sounds And also, whenever a robot sees the Red Bull, robot was abused, the robot becomes angry. But if the robot smells alcohol, in this case vodka, robot becomes happy because the robot is drunken. But this robot has a similar lung system. So gradually robot becomes serious. Then, so this is a sort of how this kind of emotional robot reacts to the environment. And okay, I should skip. Okay, now we combine the emotion extension robot and the YBN2. And you can see some gag.
続きまして、びっくりした瞬間のマスオさん。
Anyone who likes this very short gag? And this is another type of.
芝刈り機の真似。
Something like this. By the way, we, before the Corona pandemic, we collaborated for something like 10 years with the theater players. So the human robot can be useful for theater play. If you know Osamu Tezuka, in Japan, he is a god of manga. And the one theater group is playing some of his manga in the theater. So this is it is impossible by human to mimic like this. Okay, he's a director of the theater play group, and we taught them how to make a robot. So now they make this type of robotic mechanism by themselves. And now I'm in some kind of collaboration research center called Twins. It's between Waseda and the Tokyo Women's Medical University. Okay, this is a very old research, but working together with dentist people, something like 40 years ago. So I developed this kind of chewing robot because they want to analyze human chewing motion without using human, because it's a breaking of time up. Okay, sorry, I have to end. But like this, I have been doing a lot of human robot research like that. So I hope everyone here enjoyed a lot. And in the future, Japan, Taiwan, Japan has some collaboration in terms of human robot like this. So we have a lot of application like that. So thank you very much.
Thank you, Professor Takanishi, for the wonderful speech. Thank you. Please have a seat. And for our third keynote, we're honored to invite Dr. Stan Birchfield from NVIDIA, and he will present 3D scene awareness for robotic manipulation. Let's give a warm round of applause for Dr. Stan Birchfield.
Hello, everyone. Is this on? Is the microphone? Okay, there we go. Hello, everyone. Okay, so we all want robots to do useful tasks for us, like make a cup of coffee. And I used to start talks like this by asking the question of whether we were really making progress. Because from one point of view, a decade of research and the systems look kind of similar. But we have entered a new era, as you know. So I don't think that's the question anymore. We now have huge advances in hardware and software in just the last couple of years, so that we now have robots making coffee, but in a fundamentally different way. So now I think the questions are, are we done, right? Is this the end of the research? And if not, what is missing? So I'm going to propose that we need, among other things, 3D scene awareness. So the robot needs to be aware of its surroundings. And this is necessary to make sure that robots act safely, to make sure that their actions are interpretable, and also to deal with the data scarcity problem. So when we first started looking at 3D scene awareness about 10 years ago, we started with the problem of object pose estimation. Oh, is this? Okay, so about 10 years ago, we started looking at object pose estimation, and then this led to the work on DOPE, which is deep object pose estimation. So we have a deep neural network. It processes an image and detects all the instances of the object, and as well as getting the 6D pose, which is the translation and the rotation parameters. And the output of the network is then fed to an off-the-shelf PNP algorithm, and this algorithm is robust to pose, occlusion, lighting, and so forth. We trained the network solely on synthetic data. We found that a mix of domain randomization and photorealistic data achieved the best results. We need synthetic data because because it automatically gives us perfect 3D annotations, which is very hard to do with real data. And with that training, our network was then able to achieve state-of-the-art results, right, compared to previous works, and it was able to deal with extreme lighting changes, extreme poses, upside-down objects, and so forth. We then, so anyone in the world could download our code, they could run it in their lab, but only if they had the same objects that we had, and this is a problem, so we wanted to make it possible for anyone in the world to use our algorithm on their objects, and so we came up with this HOPE data set. We found some toy objects, we scanned them, the synthetic rendering is shown here on the bottom, and then we trained the model on all these objects, and so then anyone in the world could download our code with the pre-trained model weights, and they could also purchase these objects online and then do physical experiments in their lab with our code. So we're all about trying to enable other people to do their research, and so this is one of the early successes that we had. So DOPE solves the model-based problem when you already have a CAD model at training time. So you can train the network to work on that specific object. But what if you don't have that? We want foundation models. So a foundation model would enable you to do object pose estimation when you don't have the model at training time, only at test time. So this falls under the category of model-based tasks. But we also want to do model-free tasks. So if you don't have a CAD model at all, we want to be able to do 6D object pose estimation if you have a set of images of the object. So you can do static onboarding with the object sitting still on the table, or dynamic onboarding if you have the object, say, in your hand, for example. And this led to the handle data set. So we took a set of real objects, hardware tools, and kitchen instruments. We used a NERF-like process to do multi-view capture of these objects, and that enabled us to get very highly detailed, accurate 3D pixel-wise segmentation of these objects, as well as a segmentation of the handles of the objects for object affordances. And so our goal here was to support things like functional grasping. Both of these data sets, the HOPE data set and the handle data set, have been incorporated into the BOP Challenge. So we partnered with the organizers of the BOP Challenge, the benchmark for object pose. And our data sets support not only the model-based tasks, whether the objects are seen or unseen, but also the model-free tasks. So here we're showing the dynamic onboarding sequences of one of the HOPE objects. This led to our work on foundation pose. So this is a foundation model that is able to perform 6D object pose estimation on objects that it's never seen before at training time. So it handles it handles the model-based case, but it also handles model-free. So it also works if you don't have a CAD model at all. And it works on single images as well as videos. So it actually solves 4 different problems under the category of unseen. And as you can see here, we achieve state-of-the-art results on all 4 of those problems. So this is this is a render and compare algorithm. So at the bottom, you see the input image, and then we render the CAD model at a particular pose. And then we can do this in parallel on a GPU for a large number of hypothesized poses. And then it runs through a two-stage process. We have a pose refiner followed by a pose ranker. The pose refiner is a Siamese network. It takes the input crop as well as the rendering, and then has some additional layers followed by transformers that output the delta rotation and delta translation to refine the pose. And then we do this in an iterative process until it converges. And you can see it runs again in parallel on all these different poses to refine the hypotheses. And then the pose ranking network will take the output of that and perform a global assessment of all the poses that it sees in order to determine the absolute or determine the ranking from which it chooses the best pose. Okay, so we trained this model also on synthetic data only. So we use the Objaverse CAD models, and then we use LLM to add diverse textures to these objects, which enables a large-scale training data for training this network. And we were able to achieve first place on the BOP benchmark. And so we're still the #1 open source method on this benchmark. So you can go to our website, download our code, and you can use it in your lab. Okay, so this is an example of foundation pose running on a video sequence. So these are the YCB objects, and you can see that it does a good job of tracking these objects over time, even when there's severe occlusion. So if you notice the can behind the yellow mustard, even though it's severely occluded, we're still able to track it. Okay, so what if you don't have a CAD model? So this is where our bundle SDF system comes in. At the top, you can see the input video sequence. We also have, we assume that you have a mask, a 2D mask of the object in the first frame. And then this is a SLAM-based system, so it simultaneously estimates the pose of the object in each frame, as well as performing a 3D reconstruction of all the pixels that are not occluded. So here, okay, so here are some example results. You can see the high fidelity that it achieves in preserving accurate geometry, the legs of the table and the flatness of the table and so forth. It only reconstructs the pixels that it has seen. So in some of these videos, the person does not regrasp the object, and so some parts of the object are never revealed. And so we're not doing any hallucinating here. But otherwise, we would be able to recover the entire geometry. Okay, and we're a research group, but we partner with our product groups at NVIDIA, and sometimes they will take our code and they will extend it and make it even better in various ways. And so this is an example of the Bundle SDF commercialized version of Bundle SDF, in which case they have extended the code to make it better able to handle transparent objects, reflective objects, symmetric and deformable objects, and so forth. So you can go here, you can download the code. Again, you can use it in your lab, not only in a research lab, but also for commercial purposes. Okay, so we can take this Bundle SDF and we can plug it into Foundation Pose. And so instead of requiring a CAD model, even at test time, we can then take a set of reference images, produce an implicit representation of the object using a NeRF-like process, and then using neural-based rendering, use that to replace the CAD model rendering inside Foundation Pose. Everything else remains the same. This enables us to run Foundation Pose on an object that is never seen before. So this object, we take a few reference images to perform that Bundle SDF computation to get an implicit representation of the object, and then we can track the object over time, even though it doesn't have a CAD model. Here's another example of Foundation Pose doing model-free tracking on a set of objects that is never seen before, other than the reference images. Okay, and of course, there are many applications for this type of technology. So you can imagine augmented reality, where you can turn objects into games and so forth. But our real interest is in robotics. So this is a research project we did recently where we took Foundation Pose and applied it to human demonstrations in order to track the object that in the context of a task that the human was performing. And we also tracked the target object as well as the source object, and so we can get trajectories in a common coordinate frame, which we can then use to train a diffusion policy, and that enables the robot to perform tasks that were presented to it by human demonstration. So here we have, for example, pick and place tasks where there's a source object and a target object, and we want the robot to be able to manipulate them in certain ways according to the demonstrations. Okay, we can do peg and hole as well, insertion using Foundation Pose. So here we have a plug and a socket. We're tracking both of them using Foundation Pose and using that to perform the task. Foundation Pose can also be used to overcome the data scarcity problem. So here we have human demonstrations. Foundation Pose enables those demonstrations to be pulled into a simulator, and in the simulated world, we can then generate variations on the theme, and that enables us to have much larger training set than we would otherwise have. And then once we've trained the policy, we can then apply it to the real world because we have Foundation Pose matching the sim to real. Okay, but we're not only interested in object pose estimation, we also want to get a full 3D reconstruction of the environment. So some of our recent work is in that area where we recently revisited the classic stereo problem where you have a left and a right image, and you want to match those images in order to get a dense pixel-wise depth map or disparity map. So if you'd asked me a few years ago, if you'd shown me an image like this, I would have assumed that it was the result of some sort of ground truth process, but this is actually the result of our algorithm. And you can see, again, the high detail, the fidelity, and again, the denseness. So we're getting a result for every single pixel in the image. Compared to RGBD sensors, as you see on the left, our method on the right is able to do a better job of handling reflective surfaces and dark surfaces, and we also do a better job of preserving flatness of the table and that sort of thing. And again, here you can see the straightness of the lines and the 90-degree angle of the Kleenex box, and also the curvature of the mug and the handle and so forth. So again, much higher fidelity from a passive stereo algorithm. So the Foundation Stereo, it's a deep neural network. We leverage monocular depth estimation, and then we fine-tune that. Or we really adapt it. We adapt the monocular depth estimation in order to make it applicable to achieving metric depth estimation. And then after the matching, we have some follow-on blocks, conv-GRU blocks that are able then to refine the disparities to get the final output. We, again, train it only on synthetic data. So this is some examples of some of the data. And we achieved #1 on both the Middlebury and the ETH 3D data sets, or the benchmarks, the worldwide benchmarks. And again, our method is still, even though it doesn't look like #1 here, it's the #1 method for which there's open source code available. So again, you can download our code, you can use it in your lab. Okay, so there are lots of robotic applications you can imagine using Foundation Stereo for. This is, again, the result of our algorithm, object to camera pose estimation, and so forth. We're also partnering with Meta. So with their Aria glasses, they're using Foundation Stereo to achieve depth estimation, and they're going to be talking about this more next week at the ICCV conference. Okay, well, I've lost control of the display. We're using Foundation Stereo and Foundation Pose in a lot of different research projects, and we're also partnering with companies that are doing like bin picking and that sort of thing. So you saw some of these images and videos flash up here. Hopefully you can kind of make sense of them. We're also doing indiscriminate grasping and so forth. We also are interested in VLMs. So VLMs are notoriously not all that great at doing 3D queries. So if we want to know where an object is in 3D, we need to fine-tune the VLM on data with that information in it. And so here, our recent CVPR paper this year, we presented a data set called RoboSpatial that we used to fine-tune the VLM in order to get 3D, to do a better job of handling those 3D queries, answering the questions like where an object is and so forth. And so here you can see an example where we plug that into a robotic system. We're interested not only in perception, but also in control. And so we have a QRobo. QRobo is our online motion generation system that avoids collisions. It's a collision-free generation system, and you can, again, download this code, and you can use it in your robot lab. We avoid collisions by modeling both the robot and the obstacles using spheres. Makes everything fast. This is QRobo running on a real robot, following a sequence of desired poses. We can run this on an embedded GPU in real time. And well, there's more research involved. Okay, but all of that requires us to have a full 3D reconstruction of the environment, and so we have done some work on that, and this is still an active research that we're doing. And so just trying to show you, like, for example, some of the results that we can get using our 3D reconstruction algorithm. And I'm almost done. The final thing I wanted to show you is just that we're working on a new version of QRobo. It's going to be available to the public soon, so stay tuned. It makes it easy to add cost and constraints for avoiding like interpenetration and making smoother motion and so forth. None of this would be possible without our amazing researchers in my group, as well as our interns and collaborators that work with us. So shout out to them. 3D awareness is crucial for robotics. I've listed shown you a bunch of tasks that sort of fall under that umbrella. Neural reconstruction is super powerful. We have found that synthetic data is able to achieve the sim to real transfer immediately on some applications, and we predict that that'll continue in the future with more applications. And foundation models are here. And just to reiterate that our software is available both for research and commercial use in many cases. So if you can't find what you need, let me know, and I'll try to help you connect to the right person. Thank you very much.
Thank you, Dr. Birchfield, for your wonderful speech. Please have your seat. And for our fourth keynote, we are pleased to invite Professor Karen Liu, who will present the new frontier of psycho-intelligence in humanoid robotics. Let's give a round of applause for Professor Karen Liu. Welcome.
All right. It's my great honor to come back to Taiwan to give a talk, talking about my favorite topic, humanoid robots. And the best thing about being the last speaker is the question has already been answered eloquently by our previous speakers. Why humanoids? I think I'm just going to skip that, and everybody's on the same page now. A more interesting question to me is why now? This is definitely not the first time people are excited about humanoids, right? We have seen a lot of hypes before, and they just died out eventually. What makes this time different? All right, next. That's what they told me to do. Is this the answer? It's because of AI this time around, humanoids will stick? Well, I think that answers parts of the question, but to me there are other arguably more important factors at play. A lot of people would say high-density batteries, high-performance electric motors development in the last decades, they are game changers. But there are a lot of other often overlooked factors or enabling technologies, such as 3D printing, very cheap 3D printing, free online design tools, customizable PCBs, and just the cheap but still powerful on-device compute. All these new advances create this very welcoming environment for robot hobbyists to tinker, to iterate, to design, to develop robots very quickly and cheaply. And because of that, you know, we in the last few years, we have seen a lot of hobbyists become startup founders. And this collective energy and momentum is why it's driving humanoid industry today. And I think that's the reason this time around is different. So what is our vision? We recently developed an animation system that can conceptualize our vision very well. Next. So this is a digital agent, but it is fully physically simulated from head to toes, including all the fingers. And this agent can see the world, see this virtual world, and it also understand high-level natural language commands. So here we ask the agent to set up a workspace, and the agent will come up with a plan and figure out what important objects to interact in what order. And for example, you put monitors on the desk, it knows that it has to face outward, not facing the wall. And we don't need to tell this agent to do any more details planning. It will figure out everything on itself because it is connecting to a large language model, actually VLM in this case. And we can ask agent to do other things. This is a long horizon task. Ask agent to pick up the shoes, to do laundry, and that's it. You know, that's just sort of an autonomous agent we want to be able to realize in the real world. So that's our vision. And eventually, what we want to build next is a humanoid policy. And I think this is something that a lot of people share, this vision. We wanted this one policy that can do navigation, manipulation, locomotion from egocentric vision and human level natural language. Next. So how do we achieve this vision? Our bet is that we are going to solve the robotics problem using computer animation. And this is the best bet because this is the bet I know the best. My background is in computer graphics and doing animation. Next. So for example, in the past 2 decades, we've been building a lot of human digital agent models that can condition on interesting input modality. Like in this case, it would be audios, and input would be audio, output would be the human motion. Next. And during this exploration as a computer graphics researchers, I realized 2 things are really important. The first thing is not just the motion that we care about. We care about the interaction with the world. And also we want our motion to be physically generated. So what you're seeing here is not just a sequence of poses, it's a sequence of joint torques. And then we use a physics engine to realize the kinematic motion. Next. So this is what we could do in computer animation today. Next. So it sounds like if we can already physically simulate a digital agent, all we need is just push to the real world to do sim to real. So we have, can we go back to one slide? Yeah, so between human motion, between computer animation and humanoid policy, there are 4 really important gaps that we have to overcome in order to achieve a humanoid policy. And those 4 gaps, next, are embodiment gap. So even though humans and humanoids share similar morphology, but their kinematic structure, their dynamic capabilities are still very different. Next. And the second gap, I call a state to action gap. Next. We need to be able to map the poses, proprioception, to the joint torques, right? So this is something that we have to be able to learn. And then also there's the sim to real gap. We need to be able to realize the performance in sim in the real world. And finally, there is also the egocentric vision gap. This is something in computer animation we don't care too much about because we have a lot of privilege. The 3D information is readily available. But in real world, robot has to figure out from its own onboard sensors. So I'm very happy to report that. So I gave this talk 4 months ago at RSS. I'm very happy to report that the first 3 gaps are systematically overcome, especially for locomotion tasks by our recent work. Next. Next. So we have this very robust pipeline now that we start from human motion capture data. We do retargeting to create a robot motion, but this is still just kinematic motion. Those are just poses. And then we train a reinforcement learning policy that turns the poses into joint torque, the physics commands. And then we have this policy roll out and do a real zero-shot sim to real. Next. And this is what we can achieve. Next. This work is called Beyond Mimic. We basically just take a human motion capture and then train an RL policy and put it on robots. And so at this point, I'm pretty confident to say if you can do a motion capture sequence, I can make it work for robots. And you can see that the motion is very natural and realistic because this is coming directly from human motion. You probably wonder, well, you see a lot of these videos now, right? Like from Twitter, from X, Unitree, a lot of those companies, they put out this kind of videos all the time. What's the difference here? I would say the difference here is that this is not just a video. This is an open source code base, which means that everybody can just start from this. This is a new starting point. You can just directly, if you have a robot, you can directly use the code base and then you can achieve that. And that's what we wanted to do as academics because we want to be able to elevate everybody, not just our lab. Okay, so this is interesting, but every single policy you've seen so far is just a kind of not so intelligent policy because all it does is just to track that one single motion. What we want to do is to be able to track not just a single motion. We want a single policy that tracks any motion. Why do we want to do that? Because if we can track any arbitrary motion, then that means we can build a teleoperation system for humanoid. And this is inspired by a lot of the recent ongoing work from manipulation domain. Training an arbitrary policy, training a policy that can track arbitrary poses is a little bit more involved. I will skip the technical part. But once you have that policy, you could actually replace the offline motion with an online motion capture data streamed online from a operator. And then you can achieve something like this. So this is another work called Twist. Here, this robot is being teleoperated, so it's not doing all this motion by itself. There is a puppeteer behind the scene trying to coordinate this robot with the other human. So the intelligence here is a very interesting question. Is the robot really intelligent? Not really. But what the robot is capable of doing is to balance itself. You can give robots a command by doing some kind of motion, but you don't know how robot should balance because you are not robot. And robot has to figure out itself, giving these commands, how do I balance so that I could go out and shopping? Okay, I'm just gonna skip that because I have a lot more videos later. Okay, so here you can see the teleoperator. The teleoperator can just do something very free-form and arbitrary and in real time. And robot is able to just follow those poses, but at the same time knowing how to balance itself. Okay, so Twist is great. Following the full pose from an operator is something useful for teleoperation. But sometimes we don't want to give the policy the full pose. It's a little bit inconvenient. Oftentimes, we want to give the robot just a sparse command, like where your hands need to be, where your head needs to be, which direction you should turn. So we want to be able to have a policy that can just track sparse state. And with that, we were able to create a hierarchical humanoid policy where you can have high-level policy that handle vision and language, and then give out some kind of sparse, like where you should be going, where your head and hands should be. And the low-level policy will realize that into the humanoid full body. And okay, so this word called head is doing exactly that. So we have a policy that takes as input the position of the head and the orientation of the head, the 60 position of the pose of the head and the hands. And then robot will try to follow that command, but at the same time filling the rest of the body degrees of freedom by itself. So here we show that this is the first frame of what robot sees in its own camera. And then you can point at one pixel and then ask robot to go to that pixel in the real world and touch it. Okay, so that's interesting, but how do we go from tracking full state to sparse state then to any state? Because different application might demand that middle layer, the high level action space differently, right? And I don't want it to dictate what that middle layer should be. And especially right now, I actually don't know what high-level policy is. So I want to be able to have a low-level policy that's very flexible. You can give it to any state that you want to track, and the low-level policy will be able to do that. So we go back to the Beyond Mimic work. We use this RL policy to train a lot of specialized RL policies and use those policies to generate rollouts. Next. Generate a lot of data, and these data are paired observation and action data. And then you can use that to train a diffusion policy and doing some inference time guidance. This means that, next, you could control the robot by giving any command you want, as long as that command can be formulated as a function of a state, a differentiable function of state. So here we ask the robot to move in certain direction. So basically you can use a joystick control to control robot's direction. And you can also have a guidance saying that don't go to that area, but go to that green area. So you could have this kind of a goal following and avoiding obstacle kind of a scenario. Next, yeah. So here, this is what we show in the
this
real
unified
world.
policy can execute new tasks at test time 0 shot.
So what you're seeing here is that this is a combined policy, learned from many RL policies. It's a distilled policy, and this distilled policy is actually very flexible.
Simple differentiable cost functions
also very
guide the robot's motion in real time.
Yeah. So next. Next. Yeah. So this is actually a demo I like the most. So here, robot wants to go to the goal, but if you stop the robot is not going to fight you violently. It will actually just listen to you. And the reason robot can do that is because this is a multimodal generative models. So there are many modes that are all, well, the violence turned out to be the human. There are many ways to achieve the goal, and then you can change the goal in real time. All right, so now we have a lot of different kind of trackers that we design. If we embrace the notion of a system 1, system 2, you can say that at this point, we're actually pretty confident that system 1 will have solution. Now we can shift our focus to system 2. So the first question is, what is the input and output of a system 2? I think a lot of people, next, would agree that the input should include at least vision and language. There could be other things you put in there, but those are two input modalities we would love to have. But what is the output? In order to answer that question, we first have to understand how we should train system 2. So there are a lot of choices here. What data should we use to train system? Can we use human data collected in the wild? Or should we just use robot teleoperation data? Or we can use the simulation data from the world models, right? So, just like right now, because the humanoid robotics is still wide open, we have to put our bets on every single one of them. So we did all of them. So for human data collected in the wild, this is next. A good example is that project I talked about head. We had it before. Next. The vision and right now we're not dealing with the language yet, so vision and the proprioception state. But output of this system 2 should be the next, the hand position and the head position. And we will use that to directly connect to our low-level head RL policy tracker. So how do we train that system? One, the problem statement is, given a goal and a 2D image you perceive, where should you move and where should you look? If you can answer that question, then we have our system too. So we use area glosses to collect the data. So based on the short history of the videos, we want to predict the head position and head orientation. And turn out that the human data is really, really nice. Next. Because we can predict pretty well, and it catches a lot of those corner cases that would otherwise be really difficult. Next. So for example, when a person approaches a group of people in front of the wearer, it will stop its motion, it will slow down. And when the person approaches a traffic intersection, interestingly, the person will look to the left. And this is something that is very hard to program, right? You have to directly learn from data. And I bet if you use the data from UK, you will get the person looking to the right, Because the traffic flows differently. Next. Okay, so with that, we're able to do head, and we can create a system 2 and system 1. There's another way we can do it. Let's use teleoperation. So remember, we have our twist, and we can use this twist. We improve the twist so we don't need to wear the full motion capture suit. And now we can use that to teleoperate and use the data to create a basic VLA. So here is a twist 2. You can see that there's a lot of improvement. First of all, we put a camera on the head, and that camera is on a gimbal, so that means you have additional degrees of freedom to represent the neck. And we also have hands now, so robots can do some basic manipulation. Not very good hands right now, but it's this is improving. And next. All right, so I'm gonna speed this up a little bit. So the robot can do this as the basketball as well. Next. All right, can we skip the next 2 videos? All right. Next one. Okay. Now I also want to show. So I'm gonna skip all of this now. Can we just all jump to the videos, the next videos? So once the robot has a vision, we can start doing really interesting manipulation to entertain our tourists in Stanford campus.
Let me play among the stars. Let me see what spring is like on Jupiter.
All right, next. All right, so what's next? I'm just gonna be 30 seconds. So right now, as you can see, locomotion is very much handled. I wouldn't say solved. I'm resisting to say the word solved, but it's a lot of progress has been done. So the next thing I want to do is to do this again. Next, go back to the cycle again, but this time with manipulation, really manipulation, not just stretching the capability of what we have. Next. Okay, so let's play this video. So here you can see that the robot is capable of manipulating the object and locomotion as well. And doing something quite daunting. All right, final video, next one. Next one. Okay, I just want to show this one video and I'll be done. So robot manipulation, locomotion has been done, has advanced a lot in the last 3 months. All right, thank you.
Thank you, Professor Liu, and all our international speakers for your brilliant insights and sharing. 那么接下来呢，我们将进入到 panel 环节。这场对谈呢，将会由台湾大学电机工程学系的傅立成特聘教授来担任主持人。那么 AI 呢，正在成为机器人进化的关键力量，不只改变了全球产业的发展方向，也带来了全新的竞争格局。所以呢，接下来这场对谈将从国际趋势出发， 进一步的探讨台湾该如何的把握契机，发挥战略角色。那么也相信呢，待会的内容一定是精彩可期。那么接下来呢，我们要邀请到今天的语坛贵宾。Next, we move to the panel discussion, moderated by distinguished Professor Li Chen-Fu from the Department of Electrical Engineering at National Taiwan University. AI is becoming a pivotal force in the evolution of robotics, transforming global industries and introducing new competitive landscapes. So now we anticipate an engaging and insightful session. Now let's invite today's panelists to the stage. First, a warm round of applause for our moderator, distinguished Professor Li Chen-Fu from National Taiwan University. 欢迎副教授。And next, let's welcome the following panelists. Let's welcome Professor Tommy Asford again. Welcome. Let's welcome Professor Atsuo Takanishi. Welcome. Let's welcome Dr. Stan Birchfield. And next, let's welcome Professor Karen Liu. Welcome. 那接下来我们把时间交给副教授。
Okay. Good afternoon, ladies and gentlemen, and distinguished guests, speakers. It's really a true honor to be here with this full, really expert, robot experts. So today I'm going to have this last sessions with panels, and after this so exciting talks. So I'm sure that they have a lot of words they want to say besides what just presented. So before I start giving them some questions so that they can share their wisdoms, I think over the past decades, we have already experienced a remarkable journey in AI developments, witnessing the rapid evolution from predictive AI, generative AI to now to the eras of physical AIs. In this panels, all the panelists are the real experts of robotics, but we all collectively recognize that profoundly this AI. We recognize how profoundly AI has empowered service robotics on unprecedented scale. And the pace of recent advancement is truly extraordinary, leading us to believe that such AI-driven humanoid robots with certain degree of autonomy may soon become part of our everyday lives. So of course, we also understand that a humanoid robot is not a humanized robot. So while achieving the latter ones, not only we need perception, but also we need cognitions, such as the ability to feel, to reasons, and respond with understanding. In other words, there's still substantial room for research and development for us to realize these visions. Okay, so I think this is something I feel that this is also some remark I can share with everybody here. So in the following, I would like to I already prepared some questions, but some may be already answered by the speakers, but still, I believe that some you might be able to add to the questions. So I noticed that almost 3 speakers addressed the humanoid robots, but I'm sure that the purpose of having this future tech, especially our governments, want to know your visions about the AI-driven robotics. So my first question is, if you, the questions are on the papers. The question is, could you share your perspective on the developments of AI-empowered robots over the next 5 to 10 years? Okay, and also provides an approximate breakdown of the different types of general-purpose robots currently in the field based on your own classification or standard. So this is my first question to all the speakers. So if you are willing to address these questions, yeah, please feel free to do it. So who want to start with these questions? Yeah. Yes, please.
Maybe I can start. Yeah. Yeah, as you mentioned, and mentioned by the speakers today, we made really progress in the last years, thanks to advancements in many areas. Better actuation, 3D printing, PCBs, more compute resources, but also thanks to AI, to progress in AI. Many of the computer vision tasks we're dealing with in the last decades are now solved. So foundation pose, foundation stereo, and many others models, vision models, which solved hardcore problems in computer vision. And I think this will continue. I mean, we see now that we can implement more versatile tasks with robots than in the past. I mean, look at the examples what Professor Lu showed today with whole body motion, in particular locomotion, yeah. And the next step would be to combine that with manipulation, for example. So I think, yeah, AI is helping us, but AI and in particular data-driven approaches will not be, and this is my opinion, the solution for robotics. Yeah, I think we have to solve the hard problems, and one of the hardest problem in robotics is manipulation, and this is very important. If we manage to achieve the same level of progress as we did in locomotion now in manipulation, I think we'll have fantastic applications and use cases for AI-powered service robotics everywhere, not only humanoids. Yeah, I think in the next years we will have more robots applied in still structured environments or well-defined applications. And maybe in 10 to 15 years, we can talk about robots which can do professional healthcare and general purpose humanoids which can perform any task, maybe not any task, but many tasks of what humans can do. Yeah.
Fantastic. Yeah. Anyone else would like to share?
Yeah, I can add to that. Is it on?
Yes.
Okay. Agree. Yeah, that the next challenge is really combine locomotion, whole body manipulation with dexterous manipulation, and also navigation. To me, the hardest question is the how do you combine it, right? There, just from what we're doing here, there are a lot of choices, and it's really hard to predict what this system or high-level policy will do, so that we can prepare our low-level policy to be able to handle this interface in the middle. But I think that this problem will be solved. You are asking about 5 to 10 years. I think this problem will be solved next year. Just the combination of that. But there is a really big problem right now. We don't have a good hardware that has good whole body and good dexterous hands. People are improvising things right now, right? Just because, you put a really complex, heavy hands on a robot, a humanoid robot, it overheats the joints, overheats the motor right away. So there's just a lot of fundamental hardware problems that we don't have a good grasp yet. And I think once the hardware is there, software will catch up immediately.
Great. Okay, anyone else? You want to add?
Yeah, I fully agree, actually, that we still have a lot of problems in hardware development. I mean, we have to understand how to really engineer the systems from mechatronics point of view, to have systems with human-like performance, for example, in terms of torques and payload and so on. But I don't agree that the software will just be an add-on. I think we have to really develop the two things together. I think this is really important for the future, that we think about robot systems not as separation of hardware and software, but really as a joint system where software will or hardware can maybe make software easier and software and vice versa. Yeah.
Mm-hmm. Okay, fantastic. How about the awareness? Awareness for the environments in the next 5-10 years, how that will go so that this robotics can go even deeper into our life or to any service sectors?
Yeah, I can address that. So I think the big bottleneck, as we all know, is training data, right? So in robotics, we're way behind other fields in training data. And there's still an open question about whether we need more real data or synthetic data, whether the real data needs to be teleoperated with, annotated with actions, or whether we can use actionless data with online videos and that sort of thing. So I think this is still an open problem. And I guess the question of when will we get there, or I see it more of as an incremental progress, where we start with a set of well-defined tasks, we have training data for those tasks, and then we iterate until we can declare success on those tasks, and then generalize to new tasks. I guess I'm maybe not as optimistic that we'll be able to solve like a wide range of tasks in 1 year, let's say, right? But we're making good progress, and I think that'll continue.
Nakanishi-sensei.
To me, finding of users is the most important thing in the market. If the humanoids are so useful for them, they are willing to pay the money for us. Don't you think so? The one big application, I didn't have time to show you the video, but I worked with several medical person working together with Kyoto Kagaku. They are building a sort of robotics human patient simulator. So human and robot is very useful to simulate many different types of human disease. So especially for medical doctors or nurses, they have no time to learn many different types of technique in medicine. Nowadays, they are using real patient. It's so dangerous for me because in 2010, I had a heart surgery. So I needed to believe them that they are skilled enough for my heart. So anyway, humanoids can be useful for skilling up those people because you can, anytime you can fail because it's a robot, but mimics many different types of symptoms, many different types of diseases. So it's one big market for, I believe. Mm-hmm. Yeah, and disaster cases. Now Japan has a big tsunami, big earthquakes, and a volcano eruption. Many things are happening. So how do we protect our society? And also every year, many firefighters are dying. So this is a big direction for me to go to the disaster-capable robotics.
Mm-hmm.
not only humanoid, but those technologies will be useful, I believe.
Okay. Talking about the user, so it will be related to the service areas. Recently, Elon Musk predicting that they are going to produce like 10,000 Optimus in a year or two. I don't know. They are saying that making the human robot originally is our daily research that we make for example, Professor Aspel, you made Generation 7, right? So that's why we're working on the research and start also at the same time we are looking for potential users. And healthcare definitely is one. But now since people are developing all this and looking at the 30 million working forces in the world, and they use this as an estimate and try to justify the future potential profits of making these humanoid robots. I'm not sure whether the speaker, do you agree with this, that in the futures, maybe these human robots not necessarily coming into the healthcare sector, maybe into the manufacturing or working sectors as the Jensen Wang's or they predicted. How do you see that they're trying to make up the potential shortage of the working forces in the world in the next 5-10 years? How do you look at this? Can you express your ideas or your wisdom about this?
Yeah, I mean, we need technology, right? I mean, we need more automation in the society in general, everywhere. We have labor shortage, we have demographic change, and I don't think we have, and automation through robotics, humanoid robotics is one solution, yeah? But as you mentioned also, I don't think that only healthcare is healthcare is the only application of humanoids. Humanoids should be able to do any job what a human can do, also in production. It will be a huge market for humanoids, yeah? I mean, people like Musk and others, they really can analyze the markets and so on, and this is a big vision, and it will be a big market. But I want to see it first. It will take time. And I haven't seen actually things working in real. I saw only videos. And we have to be careful about the gap between videos and reality, you know, unfortunately. But I am a very optimistic person, and I wish tomorrow or in 2 years we'll have humanoids which can help in nursing homes, in production, everywhere, where in decontamination. But I think the problems are harder than what many people are claiming. Yeah. But at some point, if we solve manipulation, I think we will have these systems.
Okay. Anyone would like to share your views about?
I have a question that any manipulator that can tie shoelaces, anyone realized before? So your shoelaces, can you do that by yourself? Yes, human can do it, even small kids. But
Robots
how
can
about
do
the
that.
manipulator?
Robots. I don't know if you follow the Aloha robots, teleoperation. They train the robots. They collect a lot of data from human demonstration. Tying shoelaces is one of them, and they train a generative model to be able to tie shoelaces. So yeah, it's happening.
It's happening?
Mm-hmm.
Oh, really?
I'll show you the video, but it's a video. Yeah. Yeah, I mean, I seen that, the demo, you know, it's probably not as 100%, but they got a pretty good, you know, I don't know the percentage, but it definitely is capable of doing that, but not always.
The beginning stage is separated. The laces are separated from shoe itself.
No, well, the lace is already kind of threaded into the shoes,
yeah.
but they basically make a knot.
So there are a lot of skill should be needed for even for that simple purpose. That might.
So maybe it still takes some time, right?
Yeah, actually, I mean, in humanoids, there are so many big problems what nobody is talking about. I mean, think about the humanoids in a retirement home or in healthcare or even in production. I mean, we need a certification for this humanoid. I mean, this is not just a machine which is, in particular in healthcare. I mean, there are safety regulations which must be addressed. And I mean, maybe some people started now thinking about safety of humanoids. And the other thing is, I don't think the solution will be we need more data, we need more compute. So if we think about humans, I mean, we are very resource-aware systems. Our brain survives with few watts per day, right?
Mm-hmm.
And if we have a humanoid with 2 GPUs, whatever, I don't know how many kilowatts per day we would need, yeah, and how heavy the batteries will be, and so on. I mean, so many details, but are important. I mean, if we're claiming these robots will be at home or in production lines, we have to solve these problems too. And unfortunately, I mean, maybe we have two lines or directions in research. Some people are claiming with data and more compute, we will solve every problem. I doubt that this will be the solution. And other people may be trying to combine model-based approaches with data-driven methods so that we have the best of both worlds. But the safety issue in humanoids, energy consumption, are crucial and must be addressed before talking about introduction of this technology into any serious application.
Fantastic. Okay.
Yeah, I'll just add one thing, which is in agreement with you, Taman, that it's tempting to sort of fall into one extreme or the other, right? So one extreme is that they're like, we're almost there, and the opposite extreme is that we'll never get there, or it's going to take a lifetime. And I think the truth is probably somewhere in between, right? There are a lot of unsolved challenges. We don't know exactly how to solve these hard problems, and a lot of research is needed. And it's really anybody's guess as to how long it's going to take for these things. And so it is, I think we just have to sort of chart a course forward that takes into account, like you said, safety and so forth. And then there's also a gap between solving the technical challenges and then on the one hand, and then solving the economic challenges on the other, right? To make it economically viable, we have to have hardware that's reliable and cost efficient and so forth. When it breaks, you can repair it quickly and easily, or it doesn't break and that sort of thing. So just a lot of questions on many fronts that need to be solved.
Okay, great. Anyone want to add anything else? Okay, if not, then this question is for our governments. So what role do you think Taiwan can play in advancing the development of AI-empowered robots? And how can we further promote our industries to contribute meaningfully to society and the global communities? So if you think what could be deficient at the moment, but the policymaker, such as our governments, or you just imagine if yourself is a policymaker in your countries or organizations, what do you think is what we can do further to strengthen our chances to be better than the others? Can you share your wisdoms? Yeah, this is for, I think, our government definitely is willing to listen to any your suggestions? Yeah.
This is clear, right? This is clear, right? I mean, you have to build on the strengths of Taiwan, right? And Taiwan is the place where semiconductor industry is worldwide leading, and you have to make a point out of it, yeah, to develop key technologies for AI-based robotics, where these components for AI algorithms, for communication, for control, for learning, is maybe implemented in the hardware. Yeah, this is one strength of Taiwan. I think you should keep in mind. I mean, we get asked the same questions in Germany. You know, this is, and one important thing I would like to emphasize, actually, when it comes to strengthening industry and transfer of our research to industry. I don't have a concept actually how we can accelerate transfer from research into reality. This is a huge and big topic, but we shouldn't forget that basic research is crucial and important, and we cannot only talk about transfer. We have to keep promoting and supporting basic research, because this is the source for transfer. And maybe we have something to transfer now because we invested a lot in basic research in the past. So, and therefore my recommendation, don't forget about basic research. This is the origin where results are generated which we can transfer. And this is where we educate the next generation and talents to develop the next technologies for Taiwan, Germany, for the countries. Yeah.
Okay, great, thank you. Anyone, Karen?
There's a long term and short term, right? Short term, it's also not too short, but you know, it's more immediate. I think Taiwan should do what NVIDIA is doing, basically compete with NVIDIA. I'm not really meaning competing with it, but you just look at, you know, their grand vision. They want to own this entire stack from the hardware all the way to the AI, like the top of it. And I think Taiwan has a chance to do that too. And NVIDIA has a really good roadmap already in front of it. So this is more short term, but in the long term, I totally agree with the timing. It just, the talent pipeline is so important. Like one thing where I stand for, the most important thing to me is recruiting the best talent. And once you get them to the right place, given them the environment, they will do amazing things. So where is the pipeline in Taiwan for robotics and AI? I think that's where I would start thinking about.
Okay, great, thank you. Stan, or okay, maybe Stan first. Yeah.
I don't know what I can add to that. I mean, basic research is absolutely crucial. 100% agree. And so going forward, Taiwan should build on its strengths, right? You've got so much talent here, right, and so much expertise in semiconductors and especially, of course, and then also in just tech fields in general, that building on that strength, encouraging students to go into these areas, providing an environment in which they can thrive in inventing new technology, fostering startup companies, so assisting existing companies as well as new ones is crucial. So, yeah, I think that's where the focus needs to be. Yeah.
Okay, thank you. Takanishi Sensei.
Yeah, that's a very difficult question for me. But I am also the president of a Japanese society called Workload Users Association. That's not the technological side association, but the Users Association Robotics. So always you need to find the users if you want to extend your technology or commercialize your technology. So users is the most important thing for me to accelerate the current technology. So anyone who visited many factories in Taiwan to see, to understand what the problem of them and which direction is needed for Taiwanese companies or something. That's my opinion.
Okay. Yeah. So as a matter of fact, Taiwan is known to be very strong is the supply chain. We actually have a very strong supply chain. Of course, semiconductor is as well. But today, from all the speakers, it seems that our NSTC seems to also support that fundamental researches, basic research is really, really important. Because if we don't do now, maybe 5 years, 10 years later, we are short in that, right? So I think we not only leverage what we have, but we should not forget the fundamental research, what we should put our focus on, right? Tammy, you want to add maybe just one last?
Yeah, it's actually not only the basic research, it's the entire ecosystem which combines basic research, talents, and innovation. And I think these three things must go hand in hand. Basic research, talent, generation of the next pipeline of talents, and innovation and transfer. And these three things are important, and this is a very difficult equation. How you make progress? Actually, nobody knows that. All countries, Europe is talking about this famous ecosystem which integrates basic research, innovation, and talent generation. But there are no solutions yet. I mean, this is something what also Taiwan should think about. But yeah.
Okay, great, fantastic. I think time is up. So thank for today's wonderful. So please join me to thank all these wonderful our panelists. Okay, give them a big applause. Thank you.
Thank you for the wonderful panel. 我们再次的感谢我们的贵宾。Please stay a moment. We will take a group photo. Okay, please look at the central camera. Please stand up for the photo. Please. Okay. Okay, and one more photo for stand up to the camera. Yeah. Together, yes. Okay, and one more thumb up gesture. Thank you. Yeah. Thank you. Once again, thank you, our distinguished guest. And 非常感谢各位贵宾，大家今天热情参与，我们也感谢我们的讲者们，为我们带来非常前瞻的视野跟深刻的洞察。相信呢，大家的现场都有激发更多的思考跟合作契机。Ladies and gentlemen, thank you for your participation, and we extend our gratitude to the speakers for providing profound insights. Also, we believe today's sharing will inspire further thoughts and collaboration opportunities. Once again, thank you for your participation and have a nice day.